Everybody, and basically for the first session this afternoon, to start the workshop, we have the pleasure of welcoming Michele here, and we're going to talk about sensitivity quantification for machine learning.
Thanks a lot, and thanks everybody for joining, either in person or remote. So I've been tasked with starting this, to opening the dances for this meeting, and so I've added a few minutes of a little bit of general view on the problem of error estimation. I'm of course not particularly competent in general terms, but hopefully enough to give everyone an idea of the lie of the land. So a lot of the people here, and definitely myself, concern themselves with the modeling of chemical and material science systems. And essentially, you know, the kind of problem that we're trying to solve is being able to predict the behavior of molecule or material, and ideally to do that with no input from experiments, so that we can then, you know, even predict something about a material that has not been created yet. And perhaps also not suffer from the impact of experimental errors and uncertainty. And so if you want to do something like this, it's kind of a complicated problem, because you need to have accurate energetics and accurate properties of individual configurations of the material. And we have electronic structure theory that does this job pretty well. But you know, how accurate is electronic structure theory is problem, and the cost of electronic structure theory gets higher and higher as it gets more accurate and reliable. Furthermore, if like me, you are interested in studying you know, materials at finite temperature or in the presence of defects, getting very accurately the properties of an individual configuration is not enough, and you really need to compute the statistical averages over fluctuations that tell you something about the disorder, be it thermal or configurational, that is inherent in the system that you want to study. And so this is basically another axis in which you have two approximations and you need to use errors. So a lot of the talks at this meeting will revolve around machine learning, and it makes sense, I think, because machine learning has really been very much instrumental into making our life, at least my life, has become much easier since I've been able to sort of sidestep the calculation of electronic structure energies and more general properties. And you know, since I've been able basically to just run a few thousand calculations and then train the model and be able to do all the hundreds of thousands of single point calculations that I need to converge statistical averages. Now, all of this is very nice and exciting, but of course, each step in this procedure brings in errors and uncertainty. And it was told to me that probably this is not as universal pop knowledge as expected. Probably those who don't have kids below 10 have no idea what this is about. This is a recent Disney movie when there is a character, it's called Bruno, and nobody talks about Bruno, and it's a little bit similar. But probably I can tell whether you have kids based on whether you know about Bruno. So we need errors to be able to trust really the results of calculations, and definitely we need errors and error estimation when it comes to the electronic structure methods that form the foundations of everything that we have to create. I think that these days pretty much everything that we do is based one way or another on some electronic structure calculations, and the fact is that we don't really know. If we have a new system that nobody has studied before, we don't know how accurate we are. And this fantastic paper for a few years ago showed that actually the problem is not only of checking the error in associated with the choice of DFT or some choice of fundamental choice about your calculation, but also the details of the implementation can change results quite a bit. And also, thanks to this paper, things have improved considerably, but there is still a lot to worry about in terms of the reliability of the results that come out of electron-section calculations. So something which is very close to my heart is the issue of the quantum nature of nuclei. So pretty much, I would say probably 95% of the calculations that use molecular dynamics for sampling treat the nuclei as classical particles. And this is an approximation. Nuclei, particularly light nuclei such as hydrogen, are quantized. And depending on the problem, these can make up a very noticeable change in, let's say, this is, for instance, binding energy of a hydrogen atom in iron. This is basically the probability that the covalent OH bond fleetingly dissociates, driven entirely by quantum mechanical fluctuations. And basically, this is something where really machine learning has made a huge difference, because otherwise, if you want to simulate these things accurately, you also need to sample what is called imaginary time, and that's another dimension of computational cost. And then something which I think probably this community is a little bit less of an offender than the bio community, but converging averages and converging free energies when you perform long-time calculations is a huge issue. And at the end of the day, when you sample something, this is just a random paper, but there is always this 1 over square root of the length of the simulation, and that's slow. And that's also another source of error that we need somehow to be aware of. But so how about machine learning? So, all of these errors are kind of difficult. These are associated with the physics of your system, and so you have to test against some higher level of theory. That's pretty much the only way you can really be certain that what you're doing is accurate enough, or you need to pay the price and run for a very long time if you want to make sure that your statistics is converged. Now, machine learning I think is a little bit different in that you have a well-defined ground truth, which is what you are fitting against. And so built into the idea of doing machine learning, there is also the idea of having some level of control into the error that you're making in making this approximation. And I mean, this is why machine learning has been done also in statistics departments for a long time. And this is why, even in this field, and here I'm focusing entirely on the field of atomistic simulations, people have been trying to put some control on the error from very early on. And so, for instance, this is from 2014, but I think that this is the best figure to find, but Jörg Beller and friends have been doing this from earlier on. A very simple idea is that you generate multiple fits and you try to evaluate all of them. And when you get a discrepancy, that's an indication that something is not going well, because if these two models are meant to fit the same quantity, if they give widely different results, we have a problem. And I think we can all agree with this. And this kind of qualitative sanity check is something that people in the know have been doing for quite some time. Then Gaussian process regression is perhaps the best example. And here I'm picking a recent review, but of course the work dates back. I think Gabor, even in the 2010 you used the uncertainty. So really built into the idea of Gaussian process regression is the idea that together with the prediction of the mean, you also get a prediction of the uncertainty in your estimations. And this is something which I think hasn't been used as much as it should, but it's something which really shows how error estimation is really built into the very idea of doing machine learning. And then something which also has a long history, but I've picked a recent paper as reference because they have sort of implemented it in a fairly easy to use manner, is the idea of using error estimation to do active learning. So basically, you run your simulation, and if you have a built-in estimate of the error, every time your predicted error gets larger, you can do something about it. Typically, retrain or reweight or do something to deal with this error. And so this is really giving an idea of how having an estimate of the uncertainty is something that helps you, and it would be very nice to have the same thing for the underlying methodologies, but at least on the machine learning side, there is a lot that is available, and it's just a matter of use, basically. So now this sort of very brief overview, I hope I did decently on it. Now I want to get a little bit into what we do in my group, also to give you an idea of what we need in terms of uncertainty quantification. And so this is really just 3-4 minutes giving a broad overview of the kind of stuff that we're doing. So we have been working a lot on kind of fundamental theory of how you build representations for machine learning. So in order to do machine learning, you need to get your atomic configurations, and using the Cartesian coordinates is never a good idea because they don't have the most fundamental symmetry properties. So it's good to convert these Cartesian coordinates into something different, something more symmetric. And people have come up with many different ways of doing this. And over the past few years, we and also others, have come to the realization that actually everybody's really doing the same thing using slightly different ingredients. And we have come to the realization that basically you can regard pretty much all of the mainstream descriptors as different implementations of endpoint correlations of the atom density that are symmetrized so that they are invariant to translations, atomic permutations, and rotations. And actually, it's very easy to take this invariant framework and make it equivariant. So basically, rather than having the density correlations that are symmetrized over rotations, you add a set of spherical harmonics or something that basically relates your expansion to a fixed reference system. And so using this fixed reference system, you can expand in an equivariant way properties that are not just scalars. And this is actually something on which we have been working a lot, being able to predict dipoles, polarizabilities, densities, Hamiltonian, and so on. And something which we also have been working on is incorporating in this framework and kind of in the same language, something that can describe long-range interactions, which is tricky when you use these density correlations that are limited to a finite cutoff around each atom in your system. And very, very recently, we have also come up with this formal way of formulating also message passing frameworks as in terms of these correlations, simply pretty much by incorporating correlations that are centered on different atoms. And you can really put the same algebra that you use, that people have been used since 2007 to build descriptors that are atom-centered. You can really translate 95% of message passing in your networks into the language, in the formalism that has been used for in the field for a long time. So, what is the issue with learning equivariant properties? And this is important because it's part of what drives the structure that we're using for uncertainty quantification. So, if you want to learn equivariant properties, essentially, what you need is that you must have a model that when you rotate your physical structure is not invariant. The model must be covariant, meaning that essentially the prediction for the dipole should rotate together with the geometry of your molecule in exactly the same way. And one way of doing this using a linear regression. This is a kind of a fancy notation, but it's basically just expressing the dipole, the x, y, and z components of the dipole of molecule AI subject to a rotation in terms of a sum of some weights. So this is basically linear regression and summing over weights. And there are features that describe the structure of the molecule. And the features must have two indices, essentially. One index that is associated with enumerating them, and one that is associated with the geometry of the problem. So basically, I have a different set of features for x, y, and z. Now, if you use the same weights for X, Y, and Z, all that you need to ask is that the features themselves transform under rotations as a vector should do. If you can build features that transform in this way, and it's actually pretty easy to do that, then your model automatically, the prediction for the rotated molecule is the rotation of the predicted of the original, of the prediction for the original molecule. So basically, if you can build features with this algebraic structure, covariance is built in very naturally. And the same thing can also be done for general tensors. Basically, you exploit the fact that any tensor can be reformulated in terms of irreducible representation of SO3, which are basically spherical harmonics. And actually, this is why you need to build features or models that have this SO3 or O3 symmetry built in, because that makes it very, very easy to build models for all sorts of equivariant properties. So you can also do, fields. You can build Hamiltonians. And what is really nice is that if you build symmetry into the model, your model knows a great deal about the physics of your system. For instance, if you try to learn the Hamiltonian, this is basically a Huckel or type-binding Hamiltonian of benzene. And if you try to learn on a matrix that is full of random numbers, a symmetry adapted model cannot learn random numbers. It can only learn the part of that matrix that is consistent with this 6H symmetry. And this means that even though the energies of your electronic eigenstates are going to be random, because learning a matrix of random numbers, the degeneracies and the symmetries will be correct. And beyond that, also the response to deformations will be correct. So basically, you have Jan-Teller theorem is built into the model. When you deform a symmetric structure, the way the degeneracies break is consistent with the basic property. And so the kind of direction where we are trying to go is to use these models for tensorial properties to be able to predict all sorts of properties. And we have both a potential and a model of properties. So we can, for instance, compute IR or Raman spectra of liquid water, all using machine learning models, which is really nice because it means that, for instance, these calculations are feasible with explicit definition D. But I would have to write a 1 year long CPU time grant with the Swiss Supercomputing Center to run. Here I can basically test different DFT approximations. I can incorporate nuclear quantum effects, and this is something to run on the local cluster here at PFF. And you can also put in electronic excitations. Here, basically, we're using a prediction of the electron density of states to predict the electronic contribution to heat capacity nickel. This is a very nice paper. It's really led by Volker Deringer, and we basically just jumped in at the last minute to add some HSE quality predictions of the electron density of states. Again, something that you can do because you can predict all the properties using a machine learning model. And yeah, another very recent example here, we are doing both thermodynamics and response properties of barium titanate using a machine learning. Now, why am I telling you all of this? I'm telling you all of this because the algebraic structure of the model's implementation is a bloodiness in all of these things. And on top of everything, we also want to sample and compute thermodynamics averages. So, but at the same time, I still wanted to be able to put an error bar of my final result. So we have tried to build in uncertainty quantification in a way that is really easy and can be easily applied to the prediction, for instance, of derived properties from what you predict with your model. And the idea is super simple. We basically use, you could call it bootstrapping, even though it's not literally bootstrapping, because we don't do insertions. But basically, given a training set, what we do is very simple. We subselect, we create many training sets in which we select only 70% of the structures, and we train a committee of models. And then this is a this is basically very similar to what your Beller has been doing all along. It's a qualitative measure of whether the model can be trusted, but we try to get a more quantitative estimate of the error. And what you find is that most of the time, the qualitative behavior is correct, but the absolute magnitude of the errors don't match the actual errors. And so what we do is very, very simple. We basically use a validation set to calibrate the uncertainty prediction, effectively scaling it, so that actually there is a maximum likelihood principle, so that actually error becomes a more quantitative, so that the spread of the predictions become a more quantitative measure of actual error. And then we don't just scale the variance, but we scale individual predictions around the mean, so that we actually have an ensemble of predictions that have the right spread. And this is very useful because then anything that we do, computing a spectrum, I will give you an example in a second, we just do it separately on each prediction. And in this way, we essentially get uncertainty propagation for free. We have an ensemble of predictions, so we do whatever we need to do. And at the end of the day, we get an ensemble of end predictions, and we can put an error bar on whatever we're trying to compute. So I should add that one reason for doing this committee of resample training set is that making a prediction of the error is dirt cheap, because essentially you compute the representation, which is usually the expensive bit, only once, and then you have a committee of weights if you're doing linear regression. And so basically, to compute all of your models, you're just doing 10 scalar points. So it's really cheap to compute the different members of the committee. And the same is true also if you use a kernel method, because you have exactly the same structure. You keep the active set fixed, the calculation of the kernels is the expensive bit, and then again, the prediction of the members in the committee is just a dot product. And now this actually, this is an idea, but we never used it in practice, but in my opinion, we do the same also for a deep learning model, because the last layer, you just keep the last layer, which is linear, and basically you pre-train the network, and then you just retrain the last layer weights on different subsampled models. And it doesn't really matter, because at the end of the day, you just want to get an idea of which predictions are accurate and which are not. So how does this work? Well, first of all, this doesn't tell you the error, of course, right? If you were able to actually predict the error, you would be able to get better predictions. So this is predicting the uncertainty in your predictions. So it's perfectly normal to have large uncertainties predicted and the actual error is very small. Actually, this is a Gaussian, the most likely error is always 0. Otherwise, you have a bias and you have basically you should be able to train a better model. But what you see here, and this is for QM9, so this energy and the prediction on the error in the atomization energy, you see that basically structures from which the committee predicts a large spread have a large actual error. This is basically what this figure is telling you, which is what an uncertainty quantification data can do. And there is an example for QM9 that I really like. So in QM9, perhaps you don't know, but there are 4,000 structures that are part of the data set, but actually you should not include in your statistics because they have been flagged as problematic, because basically after they ran the geometry optimization, the bonding was not consistent with the starting bonding. So these are part of the data set but are tagged as problematic. And actually, so if you include them in your statistics, you get larger errors than in papers that don't include them. But what is nice is that if you actually make predictions for those problematic structures, they all are in the high end of the uncertainty. So, the original authors were onto something to recognize these structures as anomalous. But I think that, for most of them, actually, you can make pretty decent predictions, and the uncertainty quantification tells you that you can trust those predictions. So I think that, in a certain sense, there was no reason to discard them. You could just see that many of those had a larger uncertainty, and then everything is much better. And then, yeah, I just wanted to show you an early application. Here, we basically compute the Raman spectra by the polarizability correlation functions. And the way we are doing this is that the way we are determining the error bars on the spectra is precisely that all along the MD trajectory, we make, say, 8 polarizability predictions. So we have 8 trajectories of polarizability. We compute 8 spectra, and we compute the mean and the spread in the spectra. And this works. We had a model which was trained on paracetamol 4.1. And then we try to use the same model to make prediction on another polymorph of paracetamol, and the error bars are larger, as they should be, and the actual error is also larger. But, at least having an error bar, if we didn't have reference DFT calculations to validate these, would have given us confidence that we could trust the general shape of the peaks, even though perhaps not the intensity. So, giving you a few other ideas of what you can do by having cheap and generally applicable uncertainty quantification schemes, this is something I really like. So I don't know if this is something that is experience that has been also shared by others, but if you have a difficult system and you don't want to spend 3 years, making a potential that can really cover all the problematic regions, so something that works super well is to use a semi-empirical method as a baseline. It's easy, works. If you did this, we applied first in a project with a company, so we didn't, they didn't care about the philosophical issues. They wanted the result quickly. This works. So the way you do this is usually that you take a baseline, let's say DFTB, and you add a delta model. So you basically train on the difference between hybrid DFT and DFTB. Now, the point is that if you do this, when you exit from the confidence region, your delta learning model might have a large error, and you actually might end up getting predictions that are worse than the predictions of DFT. Typically, your system blows up still, even if you're using the baseline. So the idea that we had, which is very simple, is basically rather than building this the baseline model just by summing a delta potential to the baseline, we sum in quadrature. We sum in quadrature using an estimate of the baseline error and the point-wise estimate of the uncertainty in the machine learning prediction. The result of this is basically that whenever the model exits the safety region, the predicted error in the correction goes up, and so effectively the delta model reverts to the baseline, which is in those regions better than the correction on top of the FTP. And you can do really crazy stuff with this. So this is a replica exchange simulation of a small peptide. The model, the machine learning potential was trained on 300 Kelvin, just this protein within around. You do replica exchange up to 3000 Kelvin, this thing blows up. It has to, it decomposes. But what happens is basically rather than exploding, it reverts to the FTP, and so you actually get pretty reasonable looking fragments, and this would, for instance, make it way easier to then iteratively train your model, because the model is not falling apart, it's just reverting back to something which is not perfect, but it's reasonable. So another thing that we have done is basically trying to make this error propagation so that you can predict errors in thermodynamic energies. G of R. Okay, you want to know how the error that you're making in your potential translates into an error in your pair correlation function. So one way to do this, if you have a committee model, would be to run separate simulations with each member of the committee, compute the G of R, you do the mean, and you do the uncertainty by the spread in the predictions. But you can actually get away much more easily by just running a single simulation with the mean, and then using the statistical reweighting. This is basically theoretical law, probably 50 years old idea. So you do statistical reweighting to compute, based on the trajectory that you have run with average, what would have been the thermodynamic average had you run with one of the members of the committee that you have already computed during the trajectory. So you get all of these for free. Now, usually this reweighting expression doesn't work unless you have good overlap between the regions sampled by your potential and the potential that you want to reweight against. But the point is that we are looking for an uncertainty quantification. We are not really, we don't want a very precise prediction of the reweighted average. We just want to know, is it reasonable or is it nonsense? And so you can actually do something which is actually something that did back in 2012. One of the worst mistakes in giving a title to a paper, because we put, it's a very general result, but we put in the title for high order path integration, so nobody reads the paper. But it's actually a very general result on the statistics of this object and how you can do a cumulant expansion that allows you. You have a systematic bias, so this is not a practical strategy to get a precise value for the mean. But if all that you want is an idea of the uncertainty, it's a very good way to get a stable average of the reweighted quantity. So what can you do with these? So a couple of very quick examples. So one thing that we did was computing the phase diagram of gallium X arsenic 1 minus X. And we do this with interface spinning. So basically, we run a simulation with the coexistence of molten gallium and gallium arsenide. And we have exchanges of atoms. So basically, the system can equilibrate. It's basically, for those of you who are from materials are familiar with how you build phase diagrams. So basically, the simulation automatically establishes a lever rule where you have equilibrium between the composition of the liquid and the solid liquid fraction. And these simulations are kind of complicated. There are many pieces, and we use this software which is called IPy as sort of the hub. So we have the pinning potential computed from Plumed, and we use a committee implementation, and we have separate launch instances, and we use this basically to run. And so we do this, we get the phase diagram, and oops, there is a massive error. And now, is this the fault of DFT or is this the fault of the machine learning model? So we can actually tell, because we can do, we can basically, just by doing this reweighting idea, we can compute for each member in the committee what would be the delta mu as a function of temperature. And so we do the construction that determines the melting point, and we have 4 estimates of the melting point. And so we can separately for arsenic, gallium, and gallium arsenide put error bars on these numbers. And so we can tell that actually it is the fault of the DFT, or at least it's not the fault of the machine learning fit. Another example, this is a project which we did with a company, so otherwise why on earth we looked at catalytic hydroxylation of phenol. So basically you can attach a OH here or here, and they were interested in knowing the regioselectivity. And one of the issues is that this is done, this is acid catalyzed, and it's kind of tricky because you have weird acids in a weird environment because this thing is done in phenol. So no reasonable empirical force that works for this stuff. And also, for instance, the FTB here is really crap. So we tried the FTB, and it predicts that methane sulfonic acid would deprotonate, and we know that that's not the case. It shouldn't deprotonate so easily. And so basically, we use a delta model to correct to basically to promote the FTB to hybrid DFT accuracy. This is a monstrous calculation. We really put all the tricks of the trade. We use multiple time stepping. We have a time scale separation between a slow model that uses DFTB as a baseline and a fast model that basically does a direct prediction to DFT, but is not stable enough to run to just forget about the calculation for 3 weeks. So this is really a crazy complicated setup, but it's modular, and so it works. And we can do metadynamics to compute the dissociation of methane sulfonic acid, and we can do uncertainty quantification on the free energy profile. So basically, you can estimate what is the error due to the machine learning potential with all of this mess of multiple stepping delta models and so on and so forth. And we get confident that we have bigger problems to worry about than the accuracy of the machine learning potential. So, sort of to wrap up, so one of the things that have made it possible to do all of this is that for several years now we have been really working in a very modular fashion. So we try to have separate bits and pieces that we can combine together, so that all the stuff that we have done on path integrals, they are here, and we don't have to worry about implementing them in the real code. And then we have stuff to compute representations, to do post-processing, to visualize. If you want to try anything, it's everything in different levels of crap, but it's all available on GitHub. People who did this, these are the current people who are doing this. There are also several others who contributed a lot in the past, and nothing could be possible without them. And then, yeah, just to, many of you probably have heard the whole inductivist Turkey story already from me, so I will not repeat it, but you can look it up. It actually turns out that, of course, since Russell was in the UK, it was not an inductivist turkey, but an inductivist chicken. But the story has been taken up by the Americans and culturally adapted. So, but it's basically a story about the risk of purely inductive science, and I think that machine learning falls squarely into this risk. And so I think that one way you can try to make your machine learning models more reliable is by understanding how they work. If there are fundamental issues that prevent you from learning because of the way you build your model, what are the different ingredients that come together to form the model. But the other, not less important way is basically by having uncertainty quantification that works and try to apply it every time. So it is, I'm done. So if you have any question, there are a couple of minutes.
Thank you very much. Any questions? Any questions? Any questions? Yeah.
I'm wondering if you could go back to using the validation set to picture variances. I have just one or two quick questions.
Yes. So the idea is very simple. Basically, so in general, these committee models with bootstrapping rely on this assumption that your training set is independently identically distributed, which of course is nonsense, because there is an entire science on how you build a training set, and it's definitely not why. So, but usually, I mean, this is something that for me is very natural, because it's what happens when you try to compute errors by time averages. You have autocorrelation time, and so your error is the variance scaled by a correlation time. And so the idea is basically that we do the same. We introduce a scaling factor for the variance, and we optimize this scaling by maximizing the log likelihood over an evaluation set.
Are the statistics of the validation set similar to the training set, or do you make it different?
Yes. So you can either do a split, or actually there is an interesting thing that is actually explained very poorly in the paper. I'm sorry, I wish I could go back and explain it better. But basically, you can also use something which we call internal validation. So if you, let's say that you have 16 models, and you only use 75%. So there will be, for each sample, there will be perhaps 5 or 6 models that don't include that sample. So actually, you can include those as an internal cross-validation data set. So basically, you can use those to do the calibration. And the results are very similar to what you get with a hold-out set. So if your concern is that the validation set might have a different statistical makeup than the training set, doing that should make your concerns less.
Or even maybe the concern that if my likelihood process, my fitting process didn't generate reasonable uncertainty estimates on my training set, that maybe even using my validation set wouldn't be sufficient to have generalizable uncertainty estimates.
Yes, so at the end of the day, I feel I sleep much better knowing that what I'm trying to estimate is an error. So if I make a mistake of a factor of 2 on the error, who cares? No, it's much better than having no idea of what error. So it's, but yes, I agree with you. I think that this is something we should work more. Right? Perhaps there is a much better way to do this than what I'm doing. But this is a very simple way, and the fact that you basically only touch the training set means that you can apply to any model very easily. And this calibration is a lot of difference. I mean, to getting something good, you can really say, okay, the error is 10 MeV per atom for this structure, which I think is important because quantitative is good, but quantitative is better.
Any other questions?
Just to get it clear, so the model you're actually using in the end is trained on the whole training set,
No.
not the error. Okay.
No, the model I'm using is in a certain sense, yes, because it's the mean of the models.
Okay.
So unless you are using a very small fraction, all the training set structures will be represented somewhere. So in realistically, your model has been exposed to every structure in the training set. Okay. And actually, I read that even there are some examples in different fields in which building committee models is actually more accurate than training the model on the full figure. So I'm told.
I've forgotten, I've seen this in papers, but is this, when you quantify it against the predicted error of the gas phase?
Yeah.
If you do that in the gas phase as well. Have you ever seen that not match, or how good is this? So, because this is how, right, the committee models in your networks, this is how they differ, that you're varying something, but it's not clear.
So I think I'm not 100% certain, but I suspect that it should be possible to derive the analytical Gaussian process model as the large, some appropriate limit of this operation, I expect. Empirically, every time we try to compare, we find that as long as you also calibrate the Gaussian process certainty, because also the Gaussian process uncertainty is qualitative, it's not usually, because I think it sort of rests on the same assumptions that your training set is IID, which is not. But if you calibrate it, then the quality of the choose is much. In some cases, the GPR was better actually after calibration. In some other cases, it was worse, but comparable.
How do you treat hyperparameters? If you have a model that has hyperparameters, do you optimize those first and then only do a mean of different committees of training data? Or
So we optimize those first on the full training set.
Yeah.
And then we use exactly the same hypers for all the models because we don't want to calculate anything. Basically, we want to be able to do stuff just once. So basically, the hypers are optimized once. And I also think, so, okay, I think that from a rigorous point of view, might be better to the train, in a more Bayesian sense, train and determine the scale, for instance, simultaneously, so to use these things as a combined process. But from a practical point of view, it's so much easier basically to do whatever you used to do when you create a single model, and then you just train 85. So we are doing this in a two-step. We train our best model, and then we specify. Yeah, we multiply it.
On the topic of using the committees and the MD trajectory to estimate averages, are there assumptions I need to make about my potential unused surface? Because maybe I'm naive, but I imagine if my different estimates have slightly different metastable states, that maybe during a typical MD trajectory they go into various.
So this is an excellent question, and I actually have the best example, which is melting point calculations. So the different community models have different melting points. So if I was doing, so here actually, the fact that we are doing this, so it really, okay, so this is not something we got completely to the bottom of. Right? So clearly, if you run a separate simulation, these different community models will be impossible to evaluate because your system would fall into a complete liquid or solid. But the fact that we're doing this with these coexistence calculations, so the simulation always, even if we are 50 Kelvin undercooled, is still a solid liquid calculation because there is a pinning potential, and we are just measuring how much the system is cooled away. Okay, so this makes it possible to do this reweighting very easily. Now, I think that every case in which I don't want to apply this relies somehow on these coexistence calculations. I don't see how, for instance, you could be able to apply this if you computed absolute experience of effect. I think it would be much more. Didn't really so completely. But I think that what makes it work here is the fact that we have this consistent calculation, and we're really just changing how much thermodynamic cool the system is.
So do you think that would generalize to some sort of, if you're doing pre-energy calculations by umbrella sample, then you have a, is that?
I think that
more generalization of this idea.
I think so, because this is also exactly the same thing that happens with the dynamics. You have this biasing potential, it's very similar. It's adaptive, but it's very similar.
But the adaptive thing can make it go somewhere completely different.
Yes, but if your metadynamics has some form of converging, it must go back and forth. So it should visit both, and then you are reweighting. And there is really this additional aspect that we're using. So it's actually, it's very interesting. It's, the statistics of this object are horrible because the exponent is typically Gaussian distributed. So your weights are log normal, so they have a non-integrable tail. It's horrible. So what you basically do is say, okay, let's assume they are exactly Gaussian. If they are exactly Gaussian, you can compute everything analytically as a function of the variance. And you see it here, basically using here. This is the covariance. And so basically, if you the point is that if you try to compute, to use this cumulant expansion to compute a mean, it's not accurate because actually those states matter. But if you're just looking for order of magnitude, it's good enough or better than nothing. I don't know how negative to be, but it's good enough, I would say.
Yeah, one simple question, because I'm trying to understand how it works. These committee models, how many different models are there typically?
So
10, is it 100, is it 1,000?
So you can, here we literally use 4.
Okay.
If you use fewer than 8, you have to be careful because actually there are some subtleties, because then if you use the naive estimator, it's a biased estimator, so you have to apply some corrections. But if you have 8, then you can just, and even if you use 4, it works. Only if you use the naive estimators, then you are off by some 30%, which again is not the end of the world if you are computing an error, but there is an unbiased estimator. So
okay. And the other question is on these vibrational spectra of paracetamol,
yeah,
which you showed. So as far as I saw it, the errors are only on the intensities of the peaks, and their peaks are not shifting, or
so
is this because you only trained the intensities, or?
so okay, it's a long, okay, let me try. So there are 2 aspects. I think that there is a trivial aspect where, you know, the higher the peak, the larger the possible error. So there is some, but there is also a subtlety, and actually something that I was very unhappy with. You know, the paper had to. So the this is done with this is only half of the story, because this is done by using a single MV trajectory done with DFT and computing only the polarizabilities with a machine learning model.
Okay.
So here, the MV trajectory is just one, and actually the position of the peaks really depends from the MV trajectory. So it would be super interesting. In principle, it's possible to do this. No, actually, in principle, it's not possible. So it would be very interesting to do this also incorporating the uncertainty from the potential. The tricky aspect is that this is a time-dependent problem. Yeah. So you cannot do reweighting. You can't get the effect of potential on the dynamics in a straightforward manner. There are some, I have some ideas on how to do it, but it's tricky.
I mean, if you only need 4 different models, then you can just run 4 trajectories. So.
Yeah. Fine, but yes, okay. Perhaps we can. You tell me when I have to stop. But oh, okay. So the way this is done. So because of the need of having this calibration, okay. Because of the need of having this calibration, each of your calibrated potentials is the mean plus scaling factor times, okay? So this means that in order to compute your, I mean, you would have to compute all of the members of the committee to be able to compute the calibrated potential with which to run your single trajectory. So yes, it's doable, and okay, you know, since this is a workshop between friends, I can also be honest. So you know all of these. Okay, it's very fast. You don't pay anything. That's true in principle, but in practice, the way, because of the modularity. Because of the modularity, I run a separate lumps for each committee member. Okay, because otherwise, because it's a long story. You know, basically because of the way IPy communicates, we are fixing it, but it takes time. But yes, in principle, one could do that, and it would be a straightforward manner to. But overall would make, for instance, the calculation, then you would have to compute the properties for each of the trajectories. What is really nice in this, in this paper is that we show how you can really just run one trajectory, compute one trajectory of the properties, and you have then these 2 parts of the error, one that comes from sampling and one that comes from the property prediction, how they combine, and so you really run a single. And I think, I mean, this perhaps is also something which is worth discussing. I think that, you know, uncertainty quantification is a little bit like software development. It's something that everybody agrees that it's very important, but it's not particularly sexy. You know, it's not like the nature editor will say, "Oh, they did uncertainty quantification," then I will send it out for review.
It should be. That's why we're here, actually.
Yeah, exactly. but so my point is that I think that the ease of use of uncertainty quantified models is very important, because if you say, yeah, you can do uncertain quantification, but now you have to run 8 trajectories rather than 1. Yeah, good luck. I mean, I can't convince my own students. How am I gonna convince someone else? So I think that I would really like to push ahead and try to find a way to get also dynamics. And there are 2 aspects into dynamics. One, which is very easy. If you write a time correlation function, you have the distribution of the starting conditions and then the propagator. So one way would be basically just to reweight the starting conditions and keep the propagator to be the propagator of the mean potential. So this basically gives you different weights to different segments depending on where you start. This is basically the simplest way. You consider the actual dynamics to be driven by this, but the probability with which each segment of trajectory would contribute to the mean is reweighted according to the population of the different committee members. But I'm not convinced that that would be enough, because at the end of the day, physically, the reason why here the peaks don't move is that the position of the peaks is driven by how quickly this thing oscillates back and forth. So, changing the weight of different segments of trajectory again would modulate the intensity of the peaks, but will not really change the positions. So one thing that maybe would be interesting is to start doing this from a harmonic, looking at the errors on harmonic phonons. And then it's a stepping stone to do something where we also get the dynamics. But it's
okay. Any other question you're here online? Oh, so if not, we'll stop here. Thank you very much.
Cheers.
So what do we do, Michael? Do we go straight to the next? Right. Okay, so for the second talk, we have Stefaan Cottenier who's going to test the hell out of these.
Okay, well, the organizers gave me very precise instructions for this talk, and I want to list these instructions first to be sure that I will stick to them. They first asked to keep the talk accessible for a broad audience. No problem, that's my trademark, I will do that. They also asked to illustrate why the things in your field are done the way they are done. I can tell you in advance what the answer will be, because so far we don't know any better. And if you would have suggestions how we can do the things better, then please, that's why I'm here. Please tell those to us. The most important instruction was probably indicate where the input from the mathematics side would be useful. And so I will put some emphasis on that. And the fourth one, present problems rather than results. That's a bit harder to obey. I want to tell you some results as well. But nevertheless, let's start with the problem. So what do we want to solve? I can illustrate that with this slide that gives you the message there are just a lot of DFT codes. And if you are a DFT user, then that puts you for the problem, well, which code am I going to use? Is there one code that is better for my purpose than another one? In particular, is there one code that is more correct, more precise than another one? If you are another scientist, not in DFT, and you read papers where DFT is being used, you wonder, which code can I trust more? If they use code A, is that maybe a bad one? Should I discard that paper and rather trust the paper where they use code B? So in these questions we try to tackle. And that reminded me to a problem I faced myself when I was maybe 10 years old. The big tech of that time were pocket calculators. That was a revolution. And I was wondering as a child, well, are these right? Somebody has programmed that, and I didn't know at that time what programming was, but maybe there is one multiplication or one sum where I made a mistake. And so I was trying all kinds of sums on these pocket calculators and doing the rest, and doing also the same sum on paper, hunting for one that could be wrong. That was naive, but there is a strategy that you could use here. You could take two pocket calculators and give each of them the same task and see whether they agree. The philosophical assumption is that somehow the truth is an attractor. It would be very strange, very rare that two people make the same mistake. So as long as the two calculators agree, they are probably right. If they disagree, then one of them should be wrong, and then you can hunt for the bug. So that philosophy we try to apply to DFT codes. We take two DFT codes and we give them both the same task. For instance, calculate an energy versus volume curve, and we see whether or not these codes agree. You could do the same for electronic structure data, for phonon data, for in principle anything that DFT codes can calculate. And that is something we did in the past. You saw already a hint of this in the previous presentation. So I will summarize these methods that we applied in the past, 2016, a work that was done by a consortium of about 70 people. We never met all together. This was an online collaboration. And I like to show this picture, which was taken during the Psyche conference in 2015. That was the place where we got the largest subset of collaborators together in one place. So what did we conclude from that work? Two main conclusions. All mainstream DFT codes, they produce nearly identical results for the properties that we tested. And the second conclusion, well, that first conclusion seems like a dull conclusion, but that was actually great because that time, 2016, that was about the time when that conclusion could be made for the first time. If you go back in time and use historical versions of codes, then you see that the metrics that we were using, that they become higher and higher if you go back in time. So this good agreement was a rather recent phenomenon. Maybe you know the feeling that if you have done a project, you finished it, then you think, well, if I could just start again, then with what I know now, things will be much better. I can do it much better. And that was the feeling I got when, well, 1.5 years ago, Emanuele Bosoni and Giovanni Pizzi started to gather a new consortium to do the same game, to play the same game, but now better. So how can we do this again better? That is what I want to tell you. So what were the improvements that we do in our new approach compared to the one of 5 years ago? 3 major improvements, and the first one is the crystal set that we will use for benchmark. In the work of 2016, we used 71 crystals, and they were selected in the following way. You take these 71 elements from the periodic table, and you take their elemental ground states. So for iron, the element iron, that would be the BCC iron crystal. And for these, you are going to calculate energy versus volume curves and compare. So 71 crystals. You could argue that is not much, so therefore, in the new approach, we will take more crystals. We take every element in these 4 elemental phases, from FCC, BCC, simple cubic to diamond, in order to scan from high coordination, 12 nearest neighbors, to low coordination, 4 nearest neighbors. And we take all elements in 6 oxides. So if X is the element, then X2O is one of the oxides. That would be iron 2 oxygen. We impose the crystal structure. The crystal structure has been chosen once and for all. And by taking these particular 6 stoichiometries, you force the element X in a formal oxidation state that goes from 1 to 6. So you force it to go through a series of chemical environments. All of these 10 crystal structures, the elementary phases and the oxides, are chosen in such a way that they are all cubic, and there are no free coordinates that are not fixed by symmetry. So no forces. Cubic, that means the volume or one lattice parameter is the only geometrical degree of freedom for all of these 10 structures. That makes it very straightforward to work with for an energy versus volume curve. On top of that, rather than taking 71 elements, we take just all 96 from hydrogen to helium. Because one of the underlying goals will be to check pseudopotential libraries, and then which are you going to omit? Well, let's not omit anything, just everything from 1 to 96. So that was the first improvement, a crystal set that is different, basically larger. The second improvement is the workflow that was taken. So what do we have to calculate? 96 elements in 10 different crystal structures. And for every crystal, we take 7 energy versus volume points. So this is about 7,000 static DFT calculations. And that you want to do for many codes. So you don't want to do that manually. That is asking for human mistakes. There are solutions for that. There are workflow managers that basically behave like this. You have the problem you want to calculate, energy versus volume curve. You have some input for your DFT code. Part of that input is universal. Like I want to do it with this exchange correlation function. In our case, always PBE. Some input is specific for the codes. I want to use this pseudopotential and this basis set of that size. Well, that will depend on the DFT code you choose. So these two inputs go to your DFT codes, then you execute a particular workflow, like this energy versus volume curve, and that gives you a result. Such workflows are implemented in many environments, for instance, in the AIDA environment, which is based on quantum espresso. So if you want to do such a workflow with quantum espresso, that will be straightforward. For sure, no human mistakes. It would be nice if you could swap the magenta part, which is everything that is DFT related, with another DFT code. For instance, use entirely the same framework, but with faster. And that was exactly what a team led by Giovanni Pizzi and Nicola Marzari had done 2 years ago. It's a paper from 2021. They have written interfaces from AIDA to an entire collection of DFT codes, and therefore you can do the same AIDA workflows now with different DFT engines. And that's the perfect tool for this new precision study. So that is what we are going to use. That was the second improvement, the way how we handle the workflow. Third improvement, which metric do you use to compare results from different tools, from different codes? So what is your comparison tool? It's all about energy versus volume curve. So what are the quantities that we calculate? The curve itself, energy versus volume, which is fit by a Birch-Mergen equation. So that is sensitive to the equilibrium volume, to the curvature, the bulk modulus, and to the way how that curvature depends on the volume. So the pressure derivative of the bulk modulus, that's the B1 parameter. So these three quantities are the ones we are going to compare. And that leads just to tables with numbers. Just a small snapshot here. 2 codes, Kastep and Abinit, for the 6 aluminum oxides. All these quantities that you can fit with the Birch-Mergen equation. And you can start comparing them and see that there are only small differences. But how to summarize that entire piece of information in one number? Yeah.
Your using the absolute, so the absolute energies are meaningless here, or they are the cohesive energies?
The energies in this column are the absolute energies, and you see that this is not colored because these things cannot be
But
compared.
when you are computing also, do you compare the cohesive energies relative to the atoms, or it's not?
No, because that would require free atom calculations, which in principle can be done, but that's not a very clean DFT calculation. That would introduce another source of errors. It could be done, but it's not something we have done so far. So lots of numbers, how can we condense that to something that is more manageable, more intuitive? And in 2016, we followed this approach, the one that I will outline now. So we have our energy versus atom and volume, energy per atom versus volume per atom, two energy versus volume curves for the same crystal with two different DFT codes that in principle have different absolute values for the energies. That is the question that was just asked. That is why these curves are not on the same baseline, but because the energy is not meaningful, you just shift them to the same baseline. And we forget further on the energies. In general, these two codes will not predict exactly the same equilibrium volume. You hope that these are close, but it will not be spot on. So you have two equilibrium volumes and you take the average of that. That average equilibrium volume for these two codes, that is now a central point. That is the center of an interval plus and minus 6% relative to that reference volume. So from now on, we just work with that interval, and in that interval, we calculate the area between the two curves. If the two DFT codes would perfectly agree, then that area would be 0, and so 0 is perfect agreement. The larger that area, the larger the disagreement. And if you put that in an equation, you have the squared difference integrated over that interval, divided by the length of the interval, and square root of that. That is a quantity with as dimensions energy per atom, and that is the quantity that we always compare it. It works, it's useful, but it has limitations. And one major limitation is it's sensitive to the bulk modulus. Imagine that we have exactly that same situation that you see here on the slides, but for a crystal with a larger bulk modulus, so something like this. You see that the green area has ground. You can compare it with the old version that you see underneath. So the new green area is larger, while qualitatively the disagreement is of the same level. So you would like that this quantity is not sensitive to the bulk modulus. And that is what the new measure that we are using now takes care of. So first of all, we will not express things anymore in energy per atom versus volume per atom, but in energy versus volume. Scaling it to the number of atoms was one way of getting more comparable numbers for different kinds of crystals. And that's good for elementary crystals, but for oxides, where the number of elements is not always the same, the ratio between those elements is not always the same, that is a mess. So it would be much nicer if you can work in energy versus volume. And that will be possible with the new measure. That's the first change. We keep the same procedure of aligning the minima, of defining that average volume. But now, over that interval that we have selected in this way, we calculate the average value of the energy versus volume curve for the two codes. These quantities will not be exactly the same in general. And now we calculate for code A, the difference, the area between that mean for code A and the actual energy versus volume curve. You do the same for code B. And then you calculate the area between the two lines. And now you construct a quantity that we call epsilon from here on. Epsilon for code A versus code B, and for one particular crystal I. And that epsilon, if you translate it back to that delta quantity of the previous work, it's basically this delta quantity squared divided by a product of the squared differences with the averages. All quantities that you can get from this work.
Why so much work to define a single? I mean, you have three quantities that report on very different things, right? Volume, Buck modulus, and then so data on Buck modulus. Why don't you look separately at these three quantities? I mean, I appreciate the, why don't you look at these three quantities and then you normalize, you sum the errors, normalizing them by the mean error.
You will see some examples of that. That's of course perfectly possible, but then that's a dead end. What if you want to do other things later on? The hidden goal here is we want to have something that can be generalized to any quantity that you can calculate, even an electronic structure plot, for instance. And that is not something you can fit with just 3 parameters. So I agree that for this particular study, this is maybe a bit overkill, although it has an intuitive appeal, but its true value will become apparent if you continue and compare more quantities. The other way how to represent this epsilon value is in this way, so no reference to the delta definition anymore, so just with features that are directly available from this point. Okay, so epsilon will be a metric that we will use. Does it do what it is meant to do? Well, I can illustrate that with this example. You have here 3 different comparisons between 2 EV curves for 2 codes. One at the left-hand side with a very high bulk modulus. And that example is chosen because there the agreement between the 2 codes is very good. This middle one has a very small bulk modulus and the agreement there is not good at all. And then an intermediate bulk modulus and an agreement that is also intermediate. If you would apply that delta criterion to these 3, what do you get? Delta is smallest for the left-hand case, so best delta for the case that is intuitively the best. Delta is highest for the intermediate case, and delta is intermediate for the worst case. And that is really not what you want. Everybody would agree that middle case there, that is really the bad one. So your metric should express that. And if you do this with the epsilon metric, that is what you get. The smallest value, 0.10 at the left-hand side, 1.34 at the right-hand side, and very bad 322 in the middle. So that metric does a better job. It's not the only metric we use. There is also an alternative ID to express all these quantities as a vector in a high-dimensional space. You take the n, for instance, the volume, you take the volume difference relative to the average volume and consider that as a component of a vector. Same for the bulk modulus, same for the pressure derivative of the bulk modulus. And you can give user-defined weights to all these properties to give more emphasis to the ones you find more important. You construct that vector, and the longer the length of that vector, the larger the disagreements between the codes. The advantage of this approach is this one can be generalized to many more quantities. This is now a 3-dimensional vector, but if you have 20 quantities you want to compare, well, you can make a 20-dimensional vector, no objections. Now, this is a place where the input from people with mathematical insight can be important, because it was already touched in answer to one of the questions that was asked. So far, we have quantities with just 3 parameters, and that is still manageable. But it would be nice to have metrics that are insensitive to the number of parameters, and where you can consider in one quantity also very different objects like electronic structure curves, or density of states, or phonon density of states, or any kind of spectrum your DFT code can predict, or the list of all elastic constants. So many quantities that you can compare. How can we merge them in one meaningful metric? That would be a question I would be interested to hear the view of mathematicians on that. Let us look at a few results, because well, this data set with a set of codes has been calculated using AIDA, so we can compare results. And I want to compare first two all-electron codes. The all-electron codes that are somewhat the gold standard of DFT, the codes where you expect that the least number of numerical approximations have been made. Fleur and Wien 2K, these were the two all-electron codes in this comparison, and they calculated for these 960 crystals the three parameters from the Birch-Merton equation, and you see them here represented, as Michele suggested, as differences per quantity. What do they tell us? Look at the left-hand side at the predicted equilibrium volumes. The relative differences are peaking around 0, which is good. That means that basically these two codes agree. And the standard deviation is 0.07. So if you take an interval plus or minus 0.1% left and right of 0, then you will have all results, basically. So the expected volume uncertainty for these two LAPW codes is within 0.1%. Same curve for the bulk modulus. There, the interval is plus minus 0.5 to 1%, which makes sense because a bulk modulus is a higher derivative than an equilibrium volume. So your numerical noise amplifies. So you expect that you are worse off there. Pressure derivative of the bulk modulus, there the standard deviation is 1.3%, but that's again a higher order derivative. So that is the expected behavior. I want to emphasize that getting these data, that was very hard work by the people who run these all-electron codes. It looks like a straightforward task. You have 960 crystals, everybody runs it through the workflow manager, and you compare the results. But when you do that the first time, they agree in 95% of the cases, and there will be 5% of the cases where there are serious differences. And then you can start wondering about non-standard settings for your DFT codes, and well, they discussed and discussed until they ironed out all differences and agreed on what we expect are the true PPE DFT answers for the Birch-Merton equation for these 960 solids. And therefore, that is a precious data set that can be used now for anybody else who wants to test a new code with respect to something that is really well-grounded, well-tested. Where in the periodic table are these codes agreeing less or more? Well, here you see this epsilon metric. At the left-hand side for the 4 unary crystals, at the right-hand side for the 6 oxides. And every element is always divided in a box of either 4 or 6 sub-boxes, where you have the value for the respective crystal. If the color is magenta, then there is very good agreement. Epsilon is small. If the color is yellow, then epsilon is larger. And you see that Fleur and Wien 2K agree almost everywhere, except for the light noble gases. And that makes sense because well, this is solid neon, crystalline neon, the noble gas. Yeah, it's possible, but it's a very, very soft solid. The bulk modulus is close to 0, so the energy versus volume curve is nearly a flat line. And putting 2 flat lines on top of each other and searching for the minimum, well, this is a numerically unstable procedure. If you do this for the new quantity, you get more or less the same results. So that tells us that at least for the Birch-Merton equation, these two quantities, epsilon and mu, they carry the same meaning. Now, also, this is a place where the input from mathematicians can be useful. So we have now this more or less intuitive handmade comparison, but maybe there are mathematical tools that are better suited to capture this wealth of information. That was for two all-electron codes. We can also see now what happens if non-all-electron codes, codes that basically use pseudopotentials, are tested for the same data set. And these are the ones that have done the test so far. I can summarize them in this table, where first on these graphs you see only the Fleur and V2K results. So again, for the same three quantities, and these are these histograms that you saw on the previous slides, but just much smaller, to compare them with similar histograms from the pseudopotential codes. And there you see that the spread is a bit larger. It looks dramatic from this picture, but you will see that in practice, these spreads are not large at all. So let's pick one case, quantum espresso, where we have now this same table. It's for the oxides here, and it's the epsilon value that is compared. And you see where is it yellow, where has quantum espresso differences with respect to the all-electron codes. In the first place, in the noble gas group, which makes sense. But you also see that there are gray boxes here. So quantum espresso does not have a pseudopotential library that covers all of these 96 elements. So that is something you have to keep in mind when making these comparisons. We only compare pseudopotentials, elements that are available in the code. So somehow this comparison is limited. You could do the same for VASP. That has a similar spread as quantum espresso, and that is the table for VASP. More potentials here. So VASP has a more complete library, but a lot of yellow in the lanthanide series, which is also understandable because lanthanide pseudopotentials are often created for a particular valency, so +2 or +3. And here we are testing all formal oxidation states from +1 to +6. So it's likely that these potentials will not behave very well in some of the weird oxides. But it gives a tool for developers of potentials. If they want to make a potential for a particular oxidation state, they can do this now. This is also what happened already during this work. This is a slide from the Abilit codes. They noticed that a few of their potentials were behaving not that well, like barium. The upper row you see there. You see a lot of color, so it's between two energy versus volume curves for barium oxides. They thought, can we improve this potential? They made modifications, tried alternatives, and they settled down on the middle row, which behaves now much better. Therefore, as if the paper that will result from this work, you will never see the upper column, you will see the best value of the codes, and this improvement has been made during this process. It's the fact of having these all-electron data that are now very robust and reliable. That is the tool that people can use to improve their pseudopotentials. I think in the sake of time, I must skip a few discussions on what is the simple physics that is going on in these cubic oxides. And let me conclude. So what have we done? A new data set with 960 crystals, more elements, more environment per element, a better metric, epsilon and mu, that are more intuitive, and automation. And these three things together made it now possible to make a more thorough comparison between codes and to test in detail pseudopotentials. That is a playground not just for code improvement, but also for physics. It's it's really fun to look at the behavior of these cubic, sometimes hypothetical crystals, and to trace back what are the basic chemistry and physics that is playing a role there in that simple cubic world. We can improve on the conclusions from 2016. So then we said all mainstream codes are identical, and this is new. It didn't happen before. Now we can say, if we look better, if we look at finer details, we can start even improving the pseudopotentials. And what is in this message for you as a user, either a practitioner or somebody who reads papers about DFT? I would say it gives you peace of mind, because you can trust now that the DFT codes that are on the market are behaving well. You will, as a user, have codes with better pseudopotential libraries directly via this work or via the follow-up improvements that people will make in the coming years. And even if you use machine learning potentials, because they are always tested, trained on DFT information, well, if the DFT information is more reliable, also your machine learning potentials will inherit this reliability. Specifically for this workshop, so I could ask input from you on tools, that's mathematically grounded tools that can make this comparison even better. And see, looking at the abstracts of the coming talks, I wonder, this mathematically based DFTK code, how would that one behave if you would run the same benchmark sets? Would be very curious about that. And a global conclusion, again, this was a work with a lot of people. So thanks to the internet, thanks to the easy communication, these things are possible. And it's really true that if you collaborate, and if you collaborate with many people, you can do more. Even more so if it is well coordinated. So thanks to Emanuele and Giovanni for doing that so well. And now I'm ready for your questions.
Thank you very much. Is there any questions that we are online?
There's an online one.
Hello, this is Pascal PERNOT. Hi, Stefan. My question is, so basically here you are studying reproducibility between codes, and do you have plans to study errors when compared to accurate experimental data or something like that?
That is not our first plan, at least. I think the next step will be to study more different quantities. In the first place, electronic structure curves. So the bands, directly comparing band structures. That is a territory that is not yet explored. Comparing to experiments, well, I would be very happy if somebody would try to do so. The problem would be find very reliable experimental data for all of materials.
Yeah.
That sounds easier than it is.
Oh, yes. Thank you.
Yes.
Thanks a lot. That's really great work, and I think it's really important to have this systematic comparison. So, as someone coming more from the molecular world, the obvious question is anybody organizing something like that for molecular DFT codes? And do you think will be harder, probably, or is it easier?
Well, I will turn the question around, because one of the reasons why in 2013-14 we started with this was the feeling the chemistry people are doing such a much better job on error control than is happening in the solid state world. So we have to catch up. And the big advantage in chemistry, you have these quantum chemistry results against which you can benchmark. And you have data sets that are agreed upon in the field that people can compare on these and these and these sets of molecules. Things like this did not exist for solid state codes. So I would say, no,
the situation in the chemistry world is definitely not worse than here, not at all.
Okay.
Yeah. Yes.
I think this idea of trying to do something to quantify how good the code is for ML training is very interesting. And I've not thought of it in these terms of what you're doing, but you have the mindset and the infrastructure. I think some of the things one might measure would be quite different. And one could leverage all the infrastructure, not just the digital, the software one, but the social infrastructure that you've assembled here. For example, the DFT code could be tested to see if it's invariant to translation or rotation. Many codes are not, because they use approximations in various grids. The spread of errors due to finite K-point sampling, or when you reshape the units.
Yeah.
Massive differences. And,
That's right.
and some of these are never reported. Some of these problems are never reported. So everybody, for the past 5 years, right? You know all the people who go around saying they have so many millions of structures in their databases. I'm not thinking of individual people. I'm thinking of single person. I'm thinking of 6 or 7 people. And you download structures from there and just can't be reproduced. You try to use the same code, same version of everything, and you get milli errors, milli per atom errors, which means it's useless for ML fitting. So I think that's a great thing. And think of what to do and then exactly the thing with ML fitting is that it is different quantities, things that you're shifting of the potential, the getting rid of focusing on the physical predictions is what you're doing here, because that's what we use DFT codes for. But when you train ML models, it's exactly not those things that are worse.
Yeah. Okay, let's discuss that.
I have actually 2 questions.
So maybe very quick because we are a bit late.
Okay, so I will ask you just one, and the other we can discuss later. So have you? I mean, it's a bit of a follow-up to Gabor's question. So have you or anybody from this huge team ever tried to run ML or an ML fit on this data? And if yes, do they see discrepancies? Because usually these kind of issues that Gabor mentioned show up very clearly that you have some points that are completely outside that you can't predict at all. That actually it's not a problem of the machine learning model, but it's an inconsistency. So anyone that can...
Not as far as I know. Yeah. Be aware that there are some very strange oxides in these, so you will be venturing way out of the trusted region for your potentials. Somebody uses the name perverse oxides because they are so strange sometimes. But that makes them good test tools. You need sometimes to test something that is really different from what you are used to.
Okay, maybe in the interest of time, let's move on to the next talk. Thank you very much, Stefan, again. The next one is Pascal.
Yes.
The last talk of this session is Pascal PERNOT, University by Paris. Go ahead, Pascal.
Thank you. And I first want to thank the organizers for giving me the opportunity to present you my late developments on this validation of prediction uncertainty in computer chemistry topic. So basically, if you look at the literature of people producing prediction uncertainties with different codes, different methods, you will see that there are very different ways to approach the validation task. One is to ignore it. You publish uncertainty without validation. And basically after that, you have to either qualitative appreciation by some visual check of different properties, and some people who are really trying to do a statistical estimation of some properties to validate their prediction uncertainties. And there is a lot of development recently in the machine learning field about calibration, using the calibration sharpness framework, and I will develop that topic because it seems to me that it's a very interesting framework, even for people not doing machine learning. And I think we really need some kind of agreed upon methods to validate prediction uncertainties. So just to be brief, I want to summarize what I understand by uncertainty. So I take an extract from the GUM, which is a guide to expression of uncertain measurement. And so they tell us that in order to estimate a measurement uncertainty, it is assumed that the result of a measurement has been corrected for all recognized significant systematic effects, and that every effort has been made to identify such effects. So basically, you people working on correction of errors and so on are trying to correct these systematic effects. And basically, the uncertainty is the quantification of what's left, so the unpredictable errors, or the unpredictable part of the errors. Unpredictable, given the fact that we made our best to make the correction, and we never correct all errors. So there is always some systematic effect left. And so another point, I will be very brief about that. I'm sure you all know about these different sources of errors in computational chemistry, numerical, parametric, and model errors. And the fact is the third type is often a dominant type in non-stochastic methods. And there is no reason for the errors to be normally distributed. So that's an important point for validation methods. Never make a normality approximation assumption. And another point is to look at what we have, what are the objects on which we want to work. So some codes are able to give prediction distributions or representative samples, but most of the times you have either expanded uncertainties, such like U95, which is recommended in thermochemistry, or standard uncertainties. And given that we don't know the distribution of errors, you cannot get prediction intervals from these standard uncertainties. So we have two incompatible types of data here. There is a hand raised. Do you want to ask a question?
Not in the room.
No? Okay, so I continue then. And just a few notations. So I consider as a validation data set, so a set of predicted values of the quantity of interest that I will note V. Some form of uncertainty statement. Here this is a standard uncertainty, but this could be a 95%, U95, or even a distribution of predictions. We need reference values. And in many parts of quantum chemistry or computational chemistry, these reference values might also have uncertainty. And so we are dealing with errors, which will be the difference between the reference and the predicted value, for which we have uncertainties, UE, that might recur the combination of both uncertainties. And so prediction uncertainty quantifies the dispersion of prediction errors in some way. So I published earlier this year in GChemPhys a paper about some methods, and referee commented that these were very complex methods and they would be unlikely to be adopted by the community. So in a second reflection about that, I propose a simpler method based on a very simple diagram. For instance, if you have a heteroscedastic data set, so you don't have a single value for the uncertainty, you can plot the errors versus the uncertainties and guiding lines which are proportional to the errors, the uncertainties, excuse me. And if you do that, here I have a synthetic data set with, which is consistent. You should observe that at small uncertainties, you have small dispersion of errors. And at larger uncertainties, you observe a larger dispersion of errors. You can also draw a quantile line, for instance, for a 95 confidence interval. And here I have a normal distribution of error for my model. So you see that the quantile line runs along the k equal guideline. So this is consistent with the statistics of a normal distribution. So everything is perfect. If you have a single uncertainty, you might want to characterize, for instance, a method by giving you uncertainty of 1 kcal/mole or something like that. So what you want to plot is the z-score, so the error divided by the uncertainty. And then if you plot the z-score, the guidelines are horizontal constant lines, and you should observe that the z-score have a homogeneous distribution. Here I took the same errors than here, but instead of heteroscedastic uncertainty, I use the standard deviation of the errors. And when you see this kind of plot, you can say that you have a problem with the consistency of your errors and uncertainties. So here, everything seems okay, but you don't have any quantitative appreciation of calibration. But here you can already reject the data set or the method that gives you this uncertainty. So what is the calibration sharpness framework? So it was divided by Knighting et al. To characterize the prediction of meteorological predictions. And the framework gives important definitions of some concepts, notably calibration and sharpness. So calibration, and we say that the method is calibrated or is considered to be calibrated, is the confidence of predictions match the probability of being correct for all confidence level. So in this definition, you have a kind of assumption that you will be working with confidence intervals and so on, prediction intervals. And sharpness, what is sharpness? Is the concentration of predictive distribution in absolute terms. It is conditional to calibration. So you don't estimate sharpness if your method is not calibrated. But sharpness is a property of the predictor, of the forecast alone. It does not involve the reference data. So it's not really useful in benchmark. It's not really useful in validation. It's very useful if you have to compare several methods and choose the one which is the sharpest. So the calibrated method, you choose the sharpest, but you really cannot do validation with sharpness because there is not a limit value of sharpness that you can use to validate or not. So I proposed recently in a paper that I archived recently, the concept of tightness, where we say that a method is considered to be tight if it is calibrated for any relevant subgroup of the validation dataset. So this is a kind of small scale calibration. So calibration will be generally for the full calibration set, and you might want to look in some specific areas of your dataset if you still have calibration, and this implies the concept of tightness. So people have always been aware of the limitation of average calibration, which is implied by the first definition. And so there are stronger calibration modes that have been introduced, like group calibration, which is similar to just what I told you. You have adversarial group calibration, where you look at calibration in any random subgroup of your validation data set. There is also the concept of perfect calibration that I will speak about a little bit later. And what I proposed recently is the concept of local calibration, which is a version of group calibration, but you look at the calibration in contiguous area of a chosen coordinate for your data set that might be along the predicted value or prediction uncertainty. And if you look at the machine learning literature, you will see that there are different validation approaches that have been used or proposed. There is a very good paper, a recent paper by Scalia in 2020, which speaks about these methods. And basically, you have interval-based validation, where for a level of probability, you estimate a prediction interval at that level of probability, and you count the percentage of errors which fall within this interval. And this percentage should be equal to P. And you do that for all P values, and this corresponds to the definition of calibration as we see given by Knighting. And there is also variance-based calibration, when you estimate the variance of the errors conditional to a specific value of the uncertainty. And so I will show that actually it does not operate at the same level as interval-based validation. This is a more detailed validation approach, which more likely tests tightness than calibration. And there are also in different papers ranking-based methods, for instance, the correlation coefficient between the uncertainty and the absolute error, or confidence curves. I will present some of them, but they cannot validate calibration or tightness, because in the ranking or in the correlation coefficient, you don't have the scale which is necessary to validate tightness. But if, for instance, if you have a zero correlation coefficient between your uncertainties and your errors or your absolute errors, you can invalidate tightness. That means that your uncertainties are not reliable. So basically, just to show you how to make the test, the choice of tests generally in computational chemistry is decided by the kind of uncertainty you have. If you have an expanded uncertainty, which is the half-width of a prediction interval, you will have to use the intervals-based definition. So you define your interval, you count how many of your errors are within this interval, and we have not too large data set. There is a statistical uncertainty, so you will check if P, the target probability, is within the 95 confidence interval about this proportion, which is a binomial proportion confidence interval. And to do that, you have to avoid the normality hypothesis of the standard or textbook method, which is the VALD method, and use more advanced method, because the normal one is very bad if your data set has not normal errors. And for variance-based validation, I proposed a scheme based on this course, and which does not make any assumption about the distribution, except that it is more or less symmetric. So if you have errors which have a mean, so we are dealing with unbiased errors, so their mean is 0, and the variance is given by the square of the uncertainty, then when you compute the z-score, you should have this property. So the mean of the z-score is 0 and its variance is 1. And if you have a set of a population of z-score, you preserve these properties. So the mean of the z-score should be 0 and their variance should be 1. So to validate the z-score, you will check that 1 is within a confidence interval of the variance of z. And for that, there are adapted bootstrap methods. Again, to avoid the normality-based textbook method, which is really not good if your errors are not normally distributed. And this has the advantage to preserve the one-to-one correspondence between error and uncertainty, which you would not preserve if you compare the variance of the error to the mean squared uncertainty. Okay, which could occur. You could have an agreement by chance, but here you preserve the pairing between the errors and the uncertainty. So I think this is a more powerful validation test than simply checking the compatibility using the variance of the errors. So we have here two methods to check calibration. So to test tightness, we simply use a local calibration, and we use this calibration test on subset of the validation set along the quantity of interest or the uncertainty. So I will present the LCP analysis or the LZV analysis, which are local version of the score. The problem when you go to this local statistic is that for small data set, you increase the statistical noise. And so you have to be conscious that some of those for very small data set, you will be making tests which have no power. And so you have to be really careful of what you are doing with small data sets. And if we look at the local z-score variance testing as a function of the uncertainty, this is really similar to the reliability diagram, which is proposed by Levy et al., which use this scheme that I presented earlier about perfect calibration. So where you have to make bins of the uncertainties. Within each bin, check that the variance of the errors with these uncertainties correspond much correctly. So this is a different approach to local Z variance, but it cannot deal with homoscedastic data sets, whether here you can deal with it. So just to summarize a different method, if you have a distribution about if you have a predictive distribution, basically you can use all the methods because you will be able to estimate either the standard deviation or the confidence intervals. And there are two methods that you might find in the literature, such like calibration curves, where you need a distribution to be able to evaluate them. But all these methods will give you information about average calibration, not about tightness. Okay, and for ranking-based methods, you have no information on calibration or tightness, except if you invalidate tightness, in which case you can reject the methods. And you have basically the same kind of limitation for local methods. So LCP is a local PICP approach where it's an interval-based methods. Local Z variance, where you can estimate tightness, and also calibration, but only for very large data set, because for small data sets you have too much uncertainty to certify calibration from these split ensembles. Okay, so now I propose to you to see a few examples from the literature. The first one is one published recently by Johnny Propp and Kircher about reactivity scales. And so they provide a set of 212 errors for reaction rates by the Myers reactivity scale. So this is a rather small data set when compared to machine learning objects. And they provide U95 uncertainties values for two methods. So they propose two methods to quantify the uncertainty. And if we simply plot the errors as function of U95, you see immediately that the model B is much better than model A. I want to emphasize that Johnny and his co-author already made that similar plots, not really like those, and they also did a correct validation, calibration validation. So what I'm showing here is only showing a different aspect of the way to approach their data, but they did a really good job at uncertainty calibration validation. If I try to apply the interval-based validation to their standard, the expanded uncertainty, I can try to calculate. I didn't try. I calculate the average calibration, so that the coverage of the uncertainty, and you see that we have a probability, which is 0.995, with a statistical uncertainty too small to reach a target of 95%. So we can conclude that their method is not calibrated, and the model A and B are the same statistics. So none of the method is really calibrated. And if I look at the local calibration, I just want to show you that here, if I split this data set in 6 subsets with the same size, we have such large errors on the statistics that by looking at this alone, we could conclude that tightness is okay because the error bars covers the target value. But for tightness, as for sharpness, we have first to validate average calibration. So these data sets are not tight and they are not calibrated. But the problem when you are in these high probabilities is that you see that we have 100% coverage for most of the points. So we cannot really appreciate the extent of the problem. So we can introduce a range ratio statistic when we take the mean width of the prediction interval, and we compared it to the width of the errors in the same interval. And so I do this also for small subsets, and you see here, for instance, that the model A has intervals which are up to 10 times too large, whether model B has intervals which are about at most 2 times too large. So that's a huge improvement between model A and model B. So model B, it's much better even if it's not completely calibrated nor tight. And an interesting aspect also of this data set is if you calculate confidence curves. So confidence curves are done by estimating a statistic of the errors, like the mean absolute error. Here I normalize it by the 0 value. So it starts from 1. And you remove from the data set the largest error, a percentage of largest error, and you estimate the statistic again. So if there is a good association between uncertainties and errors, you should obtain a continuously decreasing confidence curve. Okay, which is what we got here. So even though these errors are not calibrated, they could be perfectly used, legitimately used for something like active learning, because a large uncertainty will be associated typically with large errors, or will be an indicator of possibly large errors. So you don't necessarily need a good calibration to make a good active learning methods, but you need a good confidence curve. And an interesting point also is that both models here, also they have very different calibration statistics, have exactly the same confidence curves, because one set is a monotonous transformation of the other. So the rankings are not changed. Okay, so I will skip this one because I'm advancing in time, and I want to look at the data set of 2015 by Pandey and Jacobsen about the BIF method, which is a DFT, which is assumed to give you a prediction uncertainty about the quantities of interest. And it does that by inflating the parametric uncertainty to ensure actually which I called average calibration. So we can be asked question about tightness, and this is what I will try to experiment here. So for instance, as a first plot, if we plot the error as function of the prediction uncertainty for this data set, we see that you are in problems because you see that the quantile lines do not follow, are not parallel to the guidelines. So we know that we have a problem with this data set. If I do the LZV analysis, so I should have local variance in each subset along the prediction uncertainty, which is equal to 1. And this is far to be the case. So you see that the small uncertainties are underestimated because Z-score are too large. And the large uncertainties are overestimated because their Z-score is too small. So the LZV analysis enables to conclude that the MBIF method does not provide tight uncertainty data sets. Also, you see here that the global Z variance, the average Z variance is okay. Within its uncertainty, you have 1.3 instead of 1. So as I told, I think the MBIF is an average calibrated method, but it does not give you a tightness, tight predictions. And also, if you look at the confidence curve, it is completely catastrophic, which means that there is basically no association between the amplitude of errors and the uncertainties. And so you should not use the MBIF uncertainties, at least for this property, to do active learning or something like that. This is a completely random set of uncertainties. Now Michele presented a query by committee or a committee approach to uncertainty quantification, and there was recently a very interesting paper published by Zheng et al., where they used a committee of eight neural networks to estimate formation enthalpies by two different methods. And again, a very simple way to assess if these uncertainties are prediction uncertainties is to make this kind of plot. And you see that for AEQM1, this is certainly not. It is we have very much too small uncertainties. It seems a little bit better for ANI1 CCX, but let's quantify that. Okay, so if I look at the variance of Z, for the QM1 method, it is 59 instead of 1.4. And the other one has 4.3 instead of 1.4. And here I do not use 1 as the target because we have only a small sample of 8 points. So each uncertainty should be treated as we should use the student statistic and not the standard one, which is for an infinite number of samples. And if you look at the reliability diagram, which is one way to assess tightness, it is like the LZV analysis. So we make small intervals of the standard uncertainty or the uncertainty, and we look how the standard deviation of the errors is. All points should be on the diagonal if the method is reliable. And we see that both sets are not really reliable, and that any set is more reliable than the other one. But if we look at the confidence curves, we see for both methods a sharp decrease in the 21st% of the largest uncertainties. And then it flattens out, but what the author are using this uncertainty is to identify the system with possibly large errors. So that's a kind of active learning, and they are making active learning. So their data set is really not calibrated, not tight, but still it can be used for active learning. So we don't have prediction uncertainties, but we have uncertainties that might work for some kind of usage.
So Pascal, in the interest of time, it would be good if you could.
Okay, so I have here an example for a BNN network, Bayesian neutral network, which is completely catastrophic. The confidence plot is really terrible, and the reliability diagram is also horrible. So what I want to conclude here is that calibration is easy, but tightness is tough. And you can find in the literature many methods that will give you uncertainties that you cannot really rely. And I think the calibration tightness, with this framework, you have a principal framework for UQ validation. And all people publishing uncertainties, I think, should use this kind of tool, because it is very informative about the ability of the methods to provide uncertainties. Okay, and so I just to thank you people who provided me some data set, and thank you for your attention. And also just mention that all the codes to generate the figures you saw here is available online. Thank you.
Okay, thank you very much. So, any questions?
So I have a couple of questions. So one, we use very similar plots. You have this kind of trumpet plots where you have basically on an x-axis you have the uncertainty, of the y-axis error, and you check the quantiles. So the question that I have on this is, how do you choose how tight you make the beams on the x-axis? Because here, for instance, you see these spikes at about 0.5, which probably wouldn't appear if you use the larger beams to.
Yeah, well, there are outliers. Yeah, in this set there are probably very large outliers, but basically you see here that if you well, I'm sorry, we don't, by transparency we don't see the guiding lines, but basically all your data set should be within plus or minus 3 sigma. So here you know that your uncertainties are too small.
Go back to the ones for because this one is clearly completely off.
Yeah, which one? This one?
This would look much less catastrophic.
Yes, I agree with that. It's less catastrophic.
No?
It's still too small, because you see you have too much point out of the plus or minus 3 intervals. I mean, even though the distribution are not normal, you should expect to have few points outside of a plus or minus 3 sigma interval. So in this case, from this plot you have some information. Also, if you look at the one for Johnny Prob's data, here what you give is an expanded uncertainty, so you can readily interpret those guidelines as a confidence interval. So here you should see that 5% of the points are outside of the plus or minus line. So here we can already say that his intervals his uncertainties are too large, because there is only one point which is outside of the 95% intervals. So if you have expanded uncertainty, you can really already use this as a quantitative tool. But if you have standard only things like standard deviation, like here, basically you should see that the mass of your point is within here, but mostly you should see that the dispersion of your points increases linearly with the uncertainty. That's the most important point. The dispersion of the error should increase with the uncertainty.
Okay. Any other questions? Okay, so if
It's
you-
one in the,
okay.
there's one online. Yes.
So was there a question? No.
Yes, there's one online. Only talk
Ah, online. Okay, I don't see them.
Yes, can you hear me?
Yes.
Okay, nice. Hi, Pascal. Thank you for being so critical with
okay.
our data set.
Okay, Johnny. Hi.
Yeah.
I was not critical. I use it as a good example.
but still, I mean, you could show that this is not the whole like story. And what I think it would be nice to establish like more standards so that everybody can be like more critical about their data sets.
Yeah.
So my question that I have, because this is quite advanced, what you're doing here, this is not standard practice at all. So what would be like the minimum set of like guidelines that you would recommend to the non-statisticians or non-experts that they should apply in the future to their data sets?
Okay, very nice question. Thank you. I introduce those graphs for people who are not statisticians. So there should be a first step, first introduction to validation. But if you want to get into more quantitative, so basically you should assess average calibration either by, as you did in your paper, by counting the number of points within a 95% prediction interval. This is a very reasonable and easy thing to do. Or to estimate the variance of the Z-score, which is not complex at all. I mean, you just divide the errors by the uncertainty, it takes the variance. It's one line of code. So this is the first step, to have the average calibration. But as I said, this is not sufficient. And then if you want to assess tightness, you have to go a little bit further and make groups of data. That might be groups along as we did here, groups along groups along the uncertainty, or groups along the predicted value, and do the same statistic within each group. And so if your method is tight, the statistic should be valid within each group. So it is not a very complex. It might be complex to code to get the nice graphs and so on, but in principle, it's really simple to implement. Confidence curve is a little bit more complex also, but I think if you simply adapt the level, you have a dichotomy, either interval-based or variance-based, but it depends on the information you have. If you have exponential uncertainty, you use intervals. If you have standard uncertainty, you use Z-scores, and then it's just a matter of grouping your data to check tightness, but it's not much more complex than that.
Okay, thank you.
Thank you.
Okay, so let's stop here. Thank you again.
Thank you.
Now we have the work on the.
Yeah, before we go to Pakuni, we will state that I am the current senior director. I'm sorry, because when you started, I was in the meeting, it couldn't escape. So I asked the organizers to allow me to interrupt you at the end of this first session. I always like to welcome all of you here for all the events that take place in Busan. As you are experiencing after the COVID, we are also handling events that are hybrid, like this one. And we work with organizers to try to find what is the right format to keep what is, we always try to ensure in our events, that is, you work really on open issues, that there is enough time and space for informal meetings, and you can discuss, make connections, and come back with new ideas at the end of the week. I hope this format is useful. At the end of the event, all participants receive a survey. I emphasize that for us it's very important that to receive your views on these formats and how we can improve them to be able to provide a better environment to help you to do science in this way that you can really interact in that. All of us really value this possibility to come back together after these last tough years. If you find this event, this format useful or interesting, I also take the opportunity to tell you that events like this one are selected by an independent panel of scientists from all the proposals that we received from the community. So it's really a bottom-up program where we identify what is really interesting, open, and at the edge. So if you are interested,
I want to include a few other things where we saw errors. So I tried to focus on things that don't quite work and maybe suggest some things that we're trying to do to make them work. This is not so good, but and then let me just okay, so a couple of types of errors that I guess everybody encounters in this field, as Michele already mentioned. We have some underlying physical issues describing mainly electron ground states. So this is electronic structure level. I'll refer to a couple of cases where we actually found out that these are serious problems in some of the simulations, not surprisingly. Most of the talk will be about many-body potentials and what kind of uncertainty quantification you can do there. And finally, when you get to large-scale simulations where you can extract macroscopic properties like diffusion coefficients, there's all sorts of, I guess, better understood, but still quite serious statistical issues, correlation functions, things like that. So I'll try to address each one of these. So for large-scale molecular dynamics, everybody's doing machine learning force fields, and we also started doing this a few years ago, focusing primarily on equivariant models of two flavors. So the code that we're developing are based on neural networks, so equivariant neural networks like we put on recently Allegro, and in the domain of Gaussian process regression, we developed called FLAIR, and I'll show examples for both of these. And they're open source, available if you're interested to look at some of these things. The goal, of course, is to just develop a model of a many-body function, that is the energy of positions of the atoms. So this is what we try to do. We represent some sort of a local environment around this particular atom, and then we try to capture the geometry and the species, and then try to map this sort of local environment onto a quantity which may not have physical meaning, like a local energy, then sum them up, we get a total energy, and fit to the forces by taking the derivative, we fit to the total energy that we get from ZT. So this is a common procedure that we do. So very briefly, I won't go into details, that's not the point of this. So as already mentioned, equivariant representations of atomic structure seem to be very important. And one way to do this, one way to take into account, is to develop neural networks that are not scalar, like we used to see neural networks, these or scalar valued, but actually tensor valued. So in other words, all the nonlinear sort of operations are such that they preserve what's called equivariance properties. In other words, you rotate your input and your features inside the network rotate accordingly. So the transformations commute with symmetry operations. So basically, you have a way to carry all this geometric information about orientation and whatever higher order kind of information through tensors propagated through the network, and only at the very end, you get the energy, then you backprop to the network to get the forces. So this class of equivariant neural network models that operates on this sort of tensor product math seems to be very successful in capturing accurately things like forces and energies. This is just some example benchmarks on molecules we've looked at comparing against previously developed invariant or scalar value interatomic potentials like Schneid and a few models listed here. This is not a complete list. But basically, the point is that if you include higher rank information beyond scalar, like L equals 3, this third rank tensors, you get quite high accuracy, in fact, state-of-the-art accuracy in forces and energies on molecular systems. And you can also do it with very little data, which is surprising. So one point I just want to make here is that the covariant models, if you sort of optimize them, they can learn rather quickly and not require millions and tens of thousands of data points like some previous models. What people typically think about in general, you can learn only 50 configurations and these internal-based methods. Example here. So this is the only point I want to make. Accuracy can be high, but you ask the question, so you've trained this, you've sort of tested on something that's very similar. How do these models work when you take them outside their comfort zone? And this is where sort of we really care about these kind of tests of transferability. And one example that we looked at following up on Dr. Raider's work on looking at this molecule, the 3D molecule, which has some interesting property dynamics. The test is the following: basically train it at low temperature 300 K dynamics, and you test how the model would predict forces and energies at something like 1200 K, much higher temperature, much more fluctuations that the model sees. And again, in this case, we see that great models like Equip and Allegro, there are two different flavors again of these are covariant neural networks. They outperform previous models in terms of capturing both, in the training domain, but also outside the training domain, forces and energies. Why they do so well is not quite clear. I mean, just generally seem to be quite accurate models, and they also have good transferability in this case. Okay, so very quickly, just wanted to mention that these models can also be really fast. Again, no details here. The point is that you can scale them. If you do appropriate architecture with neural network, you can scale it to hundreds of million atoms on a couple of GPUs, not a couple, 28 GPUs. But you can make them large, and you can study large dynamics, run fast simulations of, let's say, diffusion. And that's where these models start getting into trouble. So this is what sort of people, if you are working with machine learning force fields, this is something just to be aware of. And I'll start mentioning some of the issues you see that you don't see in papers, right? So things don't behave correctly. So in papers, of course, things behave correctly. So this is a diffusion simulation of lithium phosphate glass performed with the Allegro model. Very similar performance you would see with the Equip model. So these covariant neural networks capture diffusion, and you can see this sort of mean square displacement curve as a function of time on the log scale starts approaching so the Fickian diffusive regime and matches at initial MT. Let me try to say, let's try to discover something new about this material. Let's see how disorder affects ionic transport. So what do? We melt this material, we quench it at various rates to see what kind of different disorder configurations in the glass you form, and then study dynamics. And as soon as you take it to high enough temperature, well, the simulations start breaking, simply just explode. Simply because something happens to the configurations of the atoms that the model hasn't seen in the training set. And this is an annoying issue because you don't know exactly when it happens and how it happens and what kind of strategies to apply to make it better. So I mean, you can throw more training data in there, you can reduce the time step of the simulation. These are strategies we often use, going down even like 0.1 femtosecond to the time step, which should raise some eyebrows if you were doing this kind of thing. But these are helpful. But we also see that the more expensive, the more feature-rich models do better. So you take the higher rate tensors, you increase the number of radial basis function, basically enhance the resolution. The models do better, but then they get much, much slower. Okay, so these models that are sort of done to illustrate the speed and benchmarking are not sufficiently stable to run in production level study these kind of systems. So this is just sort of something that happens. Another example, even more complicated, we try to do, and this is again in the domain of electrolytes into ionic liquids, 5-component lithium ion, some anions, some other molecular species floating around, interacting strongly with ionic interactions, and then what we want to study is the diffusive properties and all sorts of correlation issues. And again, things don't work. You train them and you see, okay, so forces are very accurate. You don't need much data to train with very accurate forces. These are MeV per angstrom, very low numbers here. Energies are easy to get. There's an interesting point to be made here is that if you want to study energy and look at how the model transfers across composition states, now not the temperature domain, but across composition. In other words, you train it on, say, 10% lithium ion, and you want to test how it's done on 90% lithium ion composition. Forces work across the board even with one training point. So train here, and across the composition space, of course, is accurate. In energy domain, you train on one point, all the other energies are bad. Unless you train on two energy points, then the model somehow learns to represent different amounts of different things with only 2 points, and then it transfers to other compositions much better. This is an interesting kind of result. A posteriori, you can sort of explain the model learning some sort of chemical potential, which cannot possibly learn with one composition only. But anyhow, then we start running larger MZ, and of course things break again, unless you crank up the resolution really high and you repeat many, many times. The point of the story is that it's very difficult to make these models work in large MZ simulations unless you do a lot of iterative work to see when they work and repeat and go and update and stuff like that. So this is the reality. These machine learning force fields are not really that automatic just yet. So what can we do about this? So as Michele already mentioned, there's a class of models based on Gaussian process regression, and Albert worked on this before. These are models that are unlike neural networks. Don't just give you point estimates, they give you a posterior distribution of the prediction for which you can extract variance. How do they do it? Well, we basically operate with the concept of a kernel, so you're able to compare configurations which you're predicting with configurations of the training set. So this kernel is sort of a distance metric. And things that are far away in the configuration space will give you high uncertainty. So in other words, when you make a prediction, in neural network, you just get forces and energies. In the Gaussian process regression, you can get also uncertainty of points. And this is very helpful for doing things like active learning reduction. There are different ways of doing it. I'll just describe the latest way we're trying to do this. And this is essentially trying to construct a kernel based on some sort of feature, a high-dimensional feature that represents your atomic environment. And for this, we choose the atomic cluster expansion after a particular order. So you start with basically this ACE formula developed by Ralph Drauss. You take a particular equivariant object based on spherical harmonics and spherical basis functions here. You use the addition theorem for spherical harmonics to contract over this M index. You develop an invariant, and use this invariant, which has sort of information on where the atoms are sitting around the central atom, what flavor they are, what sort of angular geometric information exists there, and then you can construct a kernel based on these invariant descriptors. So that's one way of it. There are many ways of doing this, and there are many ways to sort of develop these features. This is just one example. Okay, then you can use Gaussian process regression, essentially using this formula from textbooks, to develop a model for local energy that is a function of the atomic environment. Okay. And then also you can get uncertainty. So uncertainty here is essentially gives you information how reliable the prediction for local energy is. So this is a kernel function with local energy prediction itself, minus the term that sort of encodes the information that you have from your training set. In this case, we use the sparsified algorithm. So you look at what information is available. If there is not enough information, then this variance becomes large. If there's a lot of information, this minus side variance gets small. So far away from training points, you have high uncertainty. Closer, you have low uncertainty. So this is a way to quantify a prediction. And this also will translate to a prediction of the force on every atom. So with every force prediction in these models, you can also get an uncertainty metric. Okay. And so, I mentioned one way. There's other ways of doing this, and there's a question: are these uncertainties meaningful? Are they relevant? Are they quantifiable? So, in another approach, we used a different type of a description of the geometry using sort of two-body and three-body. So triples and pairs of distances to represent atomic environment, again, to develop another kernel. And in these kind of approaches, basically, what you can do is construct error versus so the true error versus the predictive error, in other words, the uncertainty curves, and see that actually they track each other quantitatively. And this can be achieved by optimizing hyperparameters, the Gaussian process. If you don't do that, we found that it doesn't give you such a good quantity. So this is sort of a recipe taken from the classic book on Gaussian processes. And this is sort of the output. You develop a descriptor, build up your kernel, you train your model, optimize hyperparameters. In other words, optimizing the function likelihood. And then there is a good chance that the error, the true error, will actually be rather well predicted by the uncertainty computation process. So this is basically a test of aluminum crystal where we perturb atoms and we see how much the true error quantity strategy. So it's encouraging. And then basically that allows you to do active learning. And if you imagine sort of an algorithm that starts with an empty simulation, taking steps with an initial model that knows nothing, it will say everything is uncertain. Its uncertainty will be high. It will request automatically data from the DFT calculation, add it to a training set, retrain the model, proceed until it sees something new again when uncertainty is high again. And so this algorithm adaptively trains on the fly during an simulation, and essentially gives you a model at the very end that will have learned every new point that it sees. So you don't have to make a priori selection of your training set. It does it for you, assuming that your predictive error is good enough. So this is an example of an aluminum crystal, again, just sort of as a very, very initial example we did. Start with nothing, and then you see these black dots indicating DFT calls. The model will do this a few tens of times, and then you can see in the simulation actually has very, very few DFT calls after a while, so it has learned everything it needs to do for the solid state. Yes.
Do you incorporate additional information about the errors into the GP model, or is it only based off of distances?
So we don't actually compute the true error as we go. No.
Or on like a test set?
No. I mean, there are approaches like that where I think Alessandro did this, if I remember correctly, where they sort of run simulation and take some snapshots, look at the actual test error, when it's high enough, retrain and things like that. So that requires you to do much more work. Here the error is predicted for, otherwise it just comes from the GP. Yeah, so basically at some point we decided to melt the crystal, turn the temperature up, and the system reacts automatically by saying, oh, lots of new configurations, train again. So it calls DFT on some of the small configurations. So once you're done training the model, you can freeze the training set, and then you can map the model. This is a very important point for it. If your training set is large, and you compare your test point, every prediction, with everything in your training set, which grows, essentially this operation grows linearly with the size of the training set, you're going to have a very slow and empty simulation. So what you can do for particular structures of kernels is to freeze the training set and then map the model onto a constant cost model. You can do this for this particular quadratic dot product kernel, or a linear one, or a few other ones that we tried. Basically, with a little bit of pre-computation, you can, for a frozen training set, you can map and have a very efficient model. And the efficiency basically depends on how you decide to represent your atomic environment. In other words, what's the dimension of the descriptor here, and what is the power to do here. Again, increases accuracy at the cost of at least operational sort of stats. Importantly, also you can map the variance. I don't show the formula, they get a little bit more messy, but we have a paper on this. So you can map the variance, and that doesn't cost you that much more than predicting forces also with the map model. So you can essentially get for free a prediction. That's what we call the Bayesian force field. So you predict forces, energies, stresses, whatever you sort of decide to encode. And at the same time, even in large scale simulations, you get this constant cost prediction of the variance, which allows you to now run large scale MD, also knowing when things are unreliable. For instance, one of the sort of examples we started doing in the 2D material space. So this is a styrene material, a 2D analog of tin, I guess kind of like graphene, but tin atoms in cyano lattice. And we studied dynamics of melting and phase transformation and whatnot. And this is a map of uncertainty. In a large scale simulation, we see certain configurations appearing which were not in the training set, and they light up and indicate that something new is happening, so we need to do a little bit more retraining. So this allows you to do a hierarchical kind of approach. So you start small with a small unit cell, train, it's like adaptive sort of active learning algorithm, called DFT in a small unit cell, and then it's done. You think everything is good. You increase the size, and then at larger sizes, you see new things that you weren't able to see at smaller sizes. And then, but you see them rarely because most of the sort of microscopic dynamics is well captured. So this intermediate size, you can still put it into DFT a couple of times. So you increase the size again, and sort of do this a couple of times, and then you can end up with a model that is able to describe sort of large-scale dynamics of transformations. This is just some fun movies of standing sheet that's melting. You see sort of collapsing and disordering, and after a while it will rupture and actually go to liquid state. And at some point we didn't see sufficiently physical behavior and go back to the train. So these are two droplets, and now sort of have this necking instability and eventually merge. So these are kind of fun things you can do. If you don't go to as high temperature, so at lower temperature, what the sheet will do essentially, interestingly enough, it will collapse, disorder, but then recrystallize as bulk thin. So you can see this 2D freezing transformation that is enabled by these kind of forces. So this is just fun. For experimentalists, it's important to know what happens, because staining is actually quite interesting for topological properties, but it's very, very difficult to make devices out of. So what we find is actually quite stable. Anyhow, okay. Another interesting example where we saw a different kind of set of issues is nickel titanium. It's a knife null or shape memory alloy that a lot of groups have worked on, trying to explain the energetics of the phase transformation, which takes the material from a cubic austenite phase to lower symmetry Martin-size phase. And yeah, this is basically a material where you can distort it by hand, and the microstructure remembers this sort of interesting sort of set of twin boundaries between the different phases and things like that. And you heat it up and it recovers its original shape. So it's quite an interesting material. We wanted to train a model of it, and everybody in the field was doing PDE for these materials. So we said, okay, let's do PDE, and we were able to actually train with PDE. So this is comparison with the previous set of MEM potentials, which are of course worse because there's not machine learning. And we get all the elastic constants, everything's great. We take the material one way, the other way, we sort of train the model. And then we crank up the size. We actually want to study the phase transformation. And what happens is completely wrong. This is an example of we start with PDE at low temperature, which is sort of the right phase at low temperature. You take it up in temperature, it goes to the austenite phase. You take it down, it doesn't go to the right phase at all. It goes to some new phase with much lower volume and different symmetry. So this phase is not been characterized, never sort of detected in experiment. We try LTA, we try PDE, so only they do the same thing. So we start suspecting something wrong with the potential. Actually, this was a system where we started worrying about the accuracy of the initial flare model and went into sort of ACE-based formalism with many body sort of correlations built in, and it didn't help. So the models are still very accurate, but nothing worked unless you go to a particular functional scan, which seems to recover the right phase transformation. So this is an example of a failure of DFT due to the very delicate balance of energies between the phases, which is not unexpected in retrospect in solid phase transitions. But you have this sort of spectacular failure. Well, I shouldn't say failure. Maybe we're discovering a new phase that hasn't been found yet at high pressure. It's entirely possible. But at least in normal sort of simulations, we weren't able to do anything physically meaningful unless we went to a particular functional. Yes.
So the question is, did you compute because one of the aspects of these phase coexistence calculations is that it's yes and no, right? One phase or the other, but actually in calculations you can compute the free energy profile for the different phases, and sometimes you really see that actually your error is very small. It's just that there is a hidden phase that the error is actually really minuscule, but you get the
one
phase
cases exactly the error is quite small. Yeah, so I don't have the plot of the
because I think that's very interesting, because there are people who actually work to apply fields to stabilize these hidden phases. So it's actually interesting to find.
Yeah. So this is just an example where unless you go to large scale simulations like this, you don't see this kind of behavior. And then then you start worrying about what to do. So by some artificial tricks, we were able to stabilize the right phase, but it didn't happen. Yes.
So a little bit follow up. So on that new phase that your models went to, was the error still good on that? Were they in the training set?
Oh, yeah. Okay. The DFT was predicting this kind of behavior, so we went back.
Went back and iterated.
Yeah. So this is what PDE, LTA, PDE, that's the whole thing. Scan things differently, but it's getting the volume off, very much off. So there's no functional actually. And this is one of those examples which sort of motivates you to think about DFT functions that are better. But this is not the only example. Okay. So interestingly enough, titanium by itself is rather difficult to get with any sort of any interatomic force field that we've tried so far, even with equivariates, even with high order correlations in case, we're still unable to get titanium and a few other metals in the periodic table in just pure bulk with a single vacancy and a little bit of sort of molten structures. We cannot still get them accurate enough for our satisfaction. And this is an open question. It's one of those problems I just want to throw out that I don't want. Some metals are extremely easy. Look at copper, gold, silver, these things that we started looking at for catalytic applications. Surface reconstruction, nanoparticle material comes out beautifully. You go to other metals, you mix a little bit of bimetallic sort of composition of, a little bit of vanadium or chromium in there, and errors become all of a sudden very large. And then you look at the single metals like here, and even with an equivalent, which is the best model we've seen for molecules so far, it still gets 10% error on forces, which is not great. Flare with it, 3-body correlations is worse. We're trying to sort of go beyond it and try to find out. But there's some basic physics, which and it actually doesn't depend on the function in this case, that prevents us from very easily training, even on single metals, models that are good enough for large dynamics so far. So this is a question of why, or what do we need to do? To what level of resolution do we need to go in description? And if models will become extremely complicated and slow, is there something that can be done here? So these are sort of interesting benchmark sets which are much, much harder than molecules. Molecules were hearing that sort of the noise level and the accuracy. Here it is very, very problem. Okay, some application on reactive systems. This is sort of why we wanted to do these kind of force fields in the end, is because for reactive systems like heterogeneous catalysis, it's particularly difficult to do anything with either DFT or atomic force fields that exist. Even reactive type of force fields are not that good enough for this kind of system. So we're dropping hydrogen on the plasma surface, and a lot of hydrogen, so it's very densely covered, a lot of sort of correlations in hydrogen molecules, and we want to see what's the turnover rate of hydrogen splitting and recombining, and does it match experiment? That was the sort of the application here. And we proceed as before. We start active learning with flare based on uncertainty. You can see the red highlight the atmosphere, indicating uncertain events that called DFT. We do bulk, we do surface, with hydrogen, again, in small enough system that we can run with DFT. And automatically sort of learning this interatomic force field takes about a week of full time in serial mode. Almost no human interaction. I'll discuss in a little bit what these asterisks are. Of course, it didn't work on the first try. So, but it still gives you a sense of how long it takes. About 3 days to calculate. Most of the training actually happens on this combined system of hydrogen platform. Okay. Looking at errors, or what uncertainty does in this case. These are basically tests of the model after a straight. Now we're taking a hydrogen molecule stretch and see what's the predicted error versus what actually did. What DFT is telling us, and we see sort of expected behavior that we don't train to such large distances, so the model starts deviating here. 2 hydrogen molecules interacting with each other is okay unless you get very close. Again, the 99% confidence intervals are quite wide here, and the model starts deviating from DFT, but still, it knows that it's wrong. That's the important part. And these are tests, trained on the 111 surface. How well does the model do on 110, 100, 211 at the time surfaces? And it does worse as expected, but it tells you that it doesn't know as much about the other surfaces. And also, these tests of absorption of hydrogen of different size and different index surfaces. Again, the predictions are not bad, but in some cases the model is really unplugged, like in this case, particular site on zero surface, thanks to the it's really far away from the training set. It doesn't do poorly, but you see these kind of error bars that would raise a red flag if you were to do the project. Okay, so then we do a larger AD simulation. And this is, of course, stuff for the paper. Everything works. You get a combination of hydrogen, you can split it, you can measure rates, and fast enough, large enough simulation, you can basically just count how many times the hydrogen will split, recombine, do this as a function of temperature, extract Arrhenius activation energy compared with the experiment. It's very accurate compared to experimental measurements, which is encouraging. So this actually does work in capturing all the catalytic things. And then we wanted to push the system to much larger scale. So some demonstration system recently took to 500 billion atoms on the largest computer in the US. And on the way there, this is where sort of things started happening that you didn't see at 1,000 atoms. You see at 1,000,000 atoms, things that you don't see at 1,000 atoms. And your force fields may be okay, but if you go around large enough, you will see statistically things that you could not possibly imagine. And we do see, for instance, in the first version of the force field, platinum atoms start coming out, surrounded by hydrogens. Something unphysical, clearly, right? You don't see an experiment platinum evaporation and platinum hydride floating around. Something happened. This is at the 1,000,000 atom level simulation. For some other things like, you observe certain hydrogen atoms on the surface, and then all of a sudden it goes crazy. So we start sort of asking why this happens. And uncertainty is very helpful. At such large scale, you see these red atoms, they're uncertain. So you know that something is wrong, and the model tells you. Unlike in the neural network calculations where things just blow up and you don't know why and when, in this case, when things go wrong, you actually have a way of measuring uncertainty. And then you say, okay, maybe I didn't train large enough temperature over my platinum surface. So this is why we went back once, and this once we saw sort of problems at the 1,000,000 level, we went back and added these points that are marked by asterisks. You see at higher temperature hydrogen gas and higher temperature hydrogen platinum surface was added, and then the model became correct. So these kind of things we thought we didn't need, but we actually needed, and we only saw at large scale simulation. Very quickly, you can also do force grading, force field development, and I won't talk too much about the details here, but just conceptually, if you want to draw degrees of freedom to make your simulations even larger, like if you want to do bio, molecules, or polymers, you may not care about every single hydrogen atom. You want to force grade it away. And then there are two problems, because you are now developing a statistical model for the force field by integrating out degrees of freedom. So there's one error that is controllable and comes from the statistical averaging of the fast degrees of freedom. Then there's a second error, which is this uncertainty from the Gaussian process, which comes from your training set and the force grade configuration being sort of sufficiently diverse. And so we are finishing a project on this. Not yet published, but so the idea is to describe liquids of alkane chains with Gaussian process model for the force grade force field, integrating out the hydrogen positions, and then sort of doing this full-level active learning. And again, we sort of make sure that the uncertainty of certain models tracks sort of standard deviation of ensemble of these models, all these kind of issues become quite interesting. There are a lot of choices to be made when you go to force grading. How you force grade is sort of an unsolved problem. You postulate it. We say, okay, we're going to focus on the carbons, and we're going to call carbons differently if they're at the end of the chain than in the middle of the chain. It's an ad hoc decision, and then you have to sort of play around with these kind of strategies for various implementations, and then see what the error does at sort of large scale simulations, things like that. But this is an open problem in this field. We can develop models, but you have to somehow figure out what to do force grading dimensionality reduction step first. So there's very little work on this. It would be quite interesting to develop more sort of generic strategies. A bit more time. Just want to mention one thing that is now in the domain, not machine learning, but now in the domain of statistical analysis of indeed trajectories. And just sort of very briefly, just in case you care about ionic diffusion or any other sort of fluctuation distribution kind of points, like the read-through kind of analysis for thermal transport of viscosity, these kind of things arise, you need to simulate a very long and deep trajectory to collect enough statistics to capture your correlations. In the domain of ionic transport, which is important for batteries, we really care about how ions interact, how correlated motion happens. This is an extreme example where we found that, in the lithium-ion electrolyte, liquid lithium-ion electrolyte, ionic liquids again, the charge of lithium-ion can actually switch and become negative effectively. The dynamical charge, so the reverse sign, due to a very strong coupling with the cations. So it basically drives around with a cloud of cations because of a very strong interaction and becomes essentially a negative particle, even though lithium ions are typically positive charge. So all those kind of effects are very much driven by correlation. So how do you describe correlation in ionic diffusion? Well, if you use the mean square displacement, which is the textbook approach for diffusion coefficients, you neglect correlations. A lot of people do, but in these systems you cannot do it. The correct way to do Green-Kubo is to look at the entire charge flux correlation. There was total velocity correlations, not individual particle velocity correlation function. So in other words, what you're facing with is a statistical problem for estimating ionic conductivity is to sum the entire correlation matrix of atomic positions. And this comes out from the fact that we need to operate with sort of the center of mass. So in other words, the entire flux of a correlation. And that becomes extremely difficult to converge. You need a lot of data. So this is an example where a little math actually was able to help with reducing noise in NT simulations. And just very quickly, I wanted to mention that if you drop your off-diagonal terms of the correlation matrix, I always focus only on the particle correlation with itself and no sort of cross-particle correlations. This is the Bernstein mean square displacement formalism. You get very quick conversions, but to a wrong value. So we like all correlations completely. If you insist on doing exact Green-Kubo, it's extremely slow to converge because essentially for one big unit cell, whatever is in there, you only get one number, which is the center of mass for the whole elements. So that gives you the correct fluctuation statistics. Turns out that you can actually figure out what are the important eigenmodes of diffusion, go to that basis set of those eigenmodes, prove some theorems, which we did on neglecting certain off-diagonal terms that end up being expectation value 0. So you can actually, in expectation value, neglect them, then go back to the original correlation matrix, sum it, in other words, get the full correlated diffusion coefficient, and you could get an exact answer, but for much, much cheaper. So in other words, it's a mathematical way of reducing noise. If you again, I won't go into details here, but just going to suggest that if you look at correlation statistics in NT simulations, there are some provable approaches one can develop like this, I think, for reducing statistical noise significantly without introducing hypothesis assumptions or uncontrolled approximations, like Robert correlation terms. So if you're interested, there's a figure out from months ago. And just sort of to show you the results, again, for ionic conductors and for solid state electrolytes, the exact answer from the full Green-Kubo, full summation of the correlation matrix will be consistent with this spectral denoise approach, but will be quite different from the uncorrelated approximation. And you can actually reduce noise by a few orders of magnitude. So this is just, again, by modeling the system as a correlated Gaussian sort of, array of walkers, you can do statistical analysis and compute the variance of your diffusion coefficient prediction and prove that it actually is exactly less if you apply the spectral denoising approach compared to the full correlated estimate. Okay, finally, just maybe 5 minutes. I want to tell you a little bit of what we're trying to do to solve some of these big underlying issues with quantum mechanics. So DFT is particularly challenging when you start dealing with catalysis problems. Absorption and bulk properties in metals are very difficult to solve things to get right. Some of these phase transformations are also very subtle sort of energetic effects. So one thought has been around sort of the community, but sort of not very actively pursued just yet. Can we exchange? Can we learn to exchange correlation functionals with machine learning? Right? Can we actually do something practically useful there? And the initial point of this investigation was to say, okay, so there are some uncontrolled errors in semi-local functionals, and some exact exchange mixtures of hybrid functions do better in oxides, for defect calculations for molecules, especially in the chemical world. This is the standard. But exact exchange is quite expensive to compute, especially for set systems with trace sets and for large systems with methods as well. So the question we wanted to answer, can we learn a non-local explicit functional density that represents exactly as possible exact exchange, so we do with functional orbitals. And we want to impose on the machine learning algorithm also a exact scaling constraint that is known for the change energy. And basically start by sort of representing the density, now sort of moving from the just atom positions, now we try to represent the density. So there are non-local convolution sort of features that we develop that the density, look at its sort of geometry, and then based on these features, we build a Gaussian process model and train it to the exchange energy density. Or we also do it to the exchange energy total. And both work quite well. So basically, you start with training on small molecules, on atoms, build up this Gaussian process, repeat the same trick that we did for force fields, in other words, mapping the final model to a constant cost spline model, for instance, that doesn't explode with complexity and computational sort of cost when you increase the training set size. And then we can achieve performance that's roughly maybe a factor of 2 slower than TDE or so, implemented by CF and GPO codes. And does achieve much higher accuracy than any semi-local functional in predicting the exact exchange. It's just comparison against some hybrids and some existing semi-local functionals and CIDR if the model is evolved. Basically, what I want to show that is that there are actually possibilities in this field to learn non-local quantities like the exchange energy. And of course, we want to take it to correlation energy and so try to learn prior quantum chemistry data, which we still need to collect. But this is basically an approach that eventually can possibly solve some of these underlying error issues that plague DFT, especially for the more problematic localized electron systems. And given that this is Gaussian process regression, you could also imagine including surface quantification. We haven't done this yet, but you do get access to uncertainty with these models as well. So with this, I wanted to stop and thank everybody who contributed to this work and thank you for your attention.
We have time for one question.
Yes, question. So I really like this last bit on learning exchange energy. So exchange energy tends to be very local, right? So I expect it would be, I mean, for instance, it's not at all the same thing, but it's very easy. We tried this. So learning the difference between a GGA and a hybrid functional is very easy. Machine learning models converge very quickly with short cutoff. It's an easy problem.
As a function of atomic positions.
As a function of atomic positions.
Okay.
Yes. So I'm wondering two things. So one is the locality of exchange something that actually makes this easier? And second, how, and this is a general question that I pose myself all the time with this test learning. Maybe it's, is there any reason why learning the exchange correlation functional should be better than learning the exchange energy as a function of the atomic positions, which is something that you could also do. So is the model that should be based on the density more transferable than a model built on the atomic coordinates?
Well, yeah, we hope so. I mean, the goal here is a universal functional that can do metals and oxides and molecules. I wonder if you can actually build a model like that on atomic positions only, it would be an interesting exercise. Maybe, maybe not, I don't know.
It would be interesting to start seeing from given data set if the model built using this framework is better than a model in which you learn directly to
I agree, that would be very interesting to see.
Because you know, we can discuss this. It's the most frustrating aspect of my research over the past 2 or 3 years. You know, you build these models of the electron density, then you try to do something with that density, and most of the time it would have been easier to do directly a scalar potential like model for that target. So it would be very, but we are starting to see some indications of cases in which it helps us. So it would be very interesting to see how this is told because of like functional.
Yep.
Okay, let's thank the speaker again.